What is the distance to the nearest star? The question seems simple enough. We measure distance every day. We know how far it is to the grocery store, to the next city, to the opposite coast. But when astronomers answer this question, they do not give a number in miles or kilometers. They use a unit called the parsec. And for most people, the explanation of what a parsec actually represents makes less sense than having no answer at all. A parsec is not based on any physical object. It is not the distance light travels in a given time. It is not derived from the size of Earth or the distance to the Sun, at least not directly. Instead, a parsec is defined by an angle. Specifically, it is the distance at which an object would appear to shift by 1 arcsecond when viewed from opposite sides of Earth's orbit around the Sun. If that definition sounds backwards, that is because it is. Most units of measurement start with a length and derive other properties from it. The parsec does the opposite. It starts with an angle and works backward to define a distance. This approach confuses people because it inverts the normal relationship between observation and measurement. When we measure the distance to a building, we do not measure an angle and calculate backward. We measure the distance directly, or we pace it off, or we use a laser rangefinder. But stars are too far away for any of those methods. We cannot pace off the distance to Alpha Centauri. We cannot bounce a laser off Sirius and time its return. The only tool available to measure nearby stars is geometry, and the geometry in question relies entirely on angles, not lengths. The parsec exists because it describes what astronomers can actually observe, which is not distance but the apparent shift in a star's position as Earth moves through space. The concept of distance seems straightforward until we consider what it means in a context where nothing can be touched, paced off, or directly measured. On Earth, distance is tangible. We walk across a room and count our steps. We drive down a highway and watch the odometer. We stretch a tape measure between 2 points and read the number. Every method relies on some form of physical traverse, some way of connecting here to there with a measurable path. But space offers no such path. There is no road between Earth and the nearest star, no measuring tape long enough to span the gap, no way to physically traverse the distance and count the increments along the way. What we call distance in astronomy is not measured directly. It is inferred from observation, calculated from angles and geometry, derived from the behavior of light or the apparent motion of objects across the sky. When astronomers say a star is a certain distance away, they are not reporting a measurement in the way a surveyor reports the width of a plot of land. They are reporting the result of a calculation based on something else entirely, usually an angle or a brightness or a spectrum, and that calculation rests on layers of assumptions about how light travels, how space behaves, and how the universe is structured. The problem becomes clear when we consider what distance actually represents in the emptiness between stars. On Earth, distance is the length of a path through a medium. We measure through air, across land, over water. There is always something in between, some substance or surface that gives the space structure. But the space between stars is not empty in a simple sense, nor is it filled in a way that provides reference points. It contains scattered atoms of gas, traces of dust, occasional clouds of interstellar material, but none of this forms a continuous medium against which distance can be marked. There is no grid, no coordinate system imposed by nature itself. The concept of distance in space is an abstraction, a human construct imposed on a void that offers no inherent scale. This is why measuring cosmic distance requires a different approach than measuring terrestrial distance. On Earth, we can use standard units because we have standard objects. A meter is defined by the path light travels in a fraction of a second, but we can also build a meter stick and carry it around. We can compare lengths directly, placing one object next to another. In space, there are no meter sticks. There are no reference objects sitting at known distances that we can use for comparison. Every measurement of cosmic distance must be built from scratch, using only what we can observe from Earth, which is light, and the angles at which that light arrives. The earliest attempts to measure the distance to stars relied on the assumption that stars were similar to the Sun, just farther away. If that were true, then a star's brightness would indicate its distance. A dim star would be far away, a bright star nearby. But this assumption breaks down immediately because stars vary enormously in their intrinsic brightness. Some stars are thousands of times more luminous than the Sun. Others emit only a fraction of the Sun's light. Without knowing a star's true brightness, its apparent brightness tells us nothing about its distance. A dim star might be a faint object nearby or a brilliant object very far away. The two possibilities are indistinguishable without additional information. This problem plagued astronomy for centuries. Ancient Greek astronomers believed the stars were embedded in a sphere surrounding Earth, all at the same distance. This model was wrong, but it was consistent with observations because no one could detect any difference in distance between stars. The stars appeared as points of light scattered across the sky, and nothing in their appearance suggested that some were closer than others. Even after Copernicus proposed that Earth orbited the Sun, the distances to stars remained unknown. If Earth truly moved through space, then nearby stars should appear to shift position relative to more distant stars, an effect called parallax. But no such shift could be detected, which meant either the Earth did not move or the stars were so distant that their parallax was too small to measure with available instruments. The question of stellar distance became a test of cosmological models. If Earth orbited the Sun, parallax had to exist. The absence of detectable parallax did not disprove the heliocentric model, but it imposed a constraint. The stars had to be far enough away that their parallax fell below the threshold of measurement. Every improvement in observational precision pushed that threshold lower, and every failure to detect parallax implied that stars were even more distant than previously thought. By the 17th century, it was clear that stars were not just far away. They were so far away that the distance defied comprehension. The gap between Earth and the Sun, already vast by human standards, was trivial compared to the distance to even the nearest stars. This realization forced astronomers to confront a fundamental problem. If stars were too distant for parallax to be measured, then no direct method of determining their distance existed. Brightness was useless without knowing intrinsic luminosity. Motion across the sky, called proper motion, could be observed for some stars, but without knowing distance, proper motion could not be converted into actual velocity. Every observable property of stars was entangled with distance in a way that made the distance itself impossible to extract. The situation seemed hopeless. Astronomy could describe the positions and motions of planets with great precision, but it could not answer the most basic question about stars. How far away are they? The solution, when it finally emerged, did not come from a new technology or a more powerful telescope. It came from a recognition that the problem had been framed incorrectly. Astronomers had been trying to measure distance directly, as if stars were objects whose positions could be determined in the same way surveyors determined the positions of landmarks. But stars are not landmarks. They are light sources at unknown distances, and the only information they provide is the direction from which their light arrives. The breakthrough came from realizing that direction alone, if measured carefully enough over time, could reveal distance. Not through any single observation, but through the pattern of how a star's apparent position changed as Earth moved through its orbit. The phenomenon that makes stellar distance measurement possible is not complicated in principle. It is the same effect anyone can observe by holding up a finger at arm's length and closing one eye, then the other. The finger appears to jump against the background, shifting position relative to distant objects. The closer the finger is to your face, the larger the shift. The effect is called parallax, and it occurs whenever an object is viewed from two different positions. The apparent position of the object changes because the angle from which it is observed changes. The size of the shift depends on two factors: the distance between the two viewing positions, which astronomers call the baseline, and the distance to the object itself. For stellar parallax, the baseline is determined by Earth's orbit. As Earth moves around the Sun, an observer on Earth views the stars from continuously changing positions. Over the course of 6 months, Earth travels from one side of its orbit to the other, a distance of roughly 186 million miles. This creates a baseline far longer than any achievable on Earth's surface, but even this enormous distance is barely sufficient to produce measurable parallax for the nearest stars. The angles involved are extraordinarily small, far smaller than the resolution of the human eye, smaller even than the apparent size of features visible on the Moon through a telescope. The geometry of parallax is straightforward. Imagine a triangle with Earth at one point, the Sun at another, and a star at the third. As Earth moves from one side of its orbit to the other, the triangle's shape changes. The baseline, the distance from Earth to the Sun, forms one side of the triangle. The line from the Sun to the star forms another side, and this is the distance astronomers want to determine. The third side, from Earth to the star, is nearly the same length as the line from Sun to star because the distance to the star is so much greater than the distance from Earth to the Sun. The angle at the star, the angle between the line to Earth and the line to the Sun, is the parallax angle. In practice, astronomers measure half of this angle. They observe a star at one point in Earth's orbit, then observe it again 6 months later when Earth has moved to the opposite side of its orbit. The star appears to shift position against the background of more distant stars, which are so far away their own parallax is negligible. The amount of shift measured in angular units is twice the parallax angle. Half of this observed shift is defined as the star's parallax, and it is this quantity that appears in the definition of the parsec. The choice to use half the full shift rather than the full shift itself is a matter of convention, but it simplifies the mathematics. If a star has a parallax of 1 arcsecond, it means the star appears to shift by 2 arcseconds over 6 months. Or equivalently, the angle at the star between the line to Earth and the line to the Sun is 1 arcsecond when Earth is at its maximum displacement from the Sun. This is an almost incomprehensibly small angle. 1 arcsecond is 1/3,600th of a degree. It is the angle subtended by a dime viewed from a distance of 2.5 miles. It is smaller than the resolution limit of the human eye by a factor of more than 100. To understand why such a small angle defines a fundamental unit of distance, we need to examine the relationship between angular measurements and linear measurements in geometry. When an object is far away, small changes in its position produce even smaller changes in the angle from which it is viewed. The relationship is inverse. Double the distance to an object and its parallax angle is cut in half. Triple the distance and the parallax is reduced to 1/3. This inverse relationship means that parallax is most useful for nearby objects and becomes progressively less useful as distance increases. At some point, the parallax angle becomes so small that it cannot be measured reliably, and beyond that point, parallax is useless as a distance indicator. The parsec is defined as the distance at which an object has a parallax of exactly 1 arcsecond. This definition ties the unit directly to what can be observed. It does not start with a distance and ask what parallax that distance would produce. It starts with a measurable parallax and defines the distance that corresponds to it. This is why the parsec feels backwards. It treats angle as the fundamental quantity and distance as the derived quantity, which is the opposite of how humans intuitively think about space. We think of distance as primary and angle as something that depends on distance. But in astronomy, angle is what we measure, and distance is what we calculate from it. The actual distance represented by 1 parsec can be calculated using trigonometry. The baseline is the distance from Earth to the Sun, approximately 93 million miles, or 1 astronomical unit. The parallax angle is 1 arcsecond, which is 1/3,600th of a degree, or about 0.00004848 radians. For small angles, the tangent of the angle is approximately equal to the angle itself when measured in radians. This means the distance to the star is approximately the baseline divided by the angle in radians. Plug in the numbers, and 1 parsec works out to about 19 trillion miles, or roughly 3.26 light years. The light year is more familiar to most people because it is based on a comprehensible concept. Light travels at a fixed speed, and a light year is the distance light covers in 1 year. This makes intuitive sense. The parsec, by contrast, is based on an obscure geometric relationship involving an angle most people have never heard of and a baseline defined by Earth's orbit. It seems unnecessarily complicated, a relic of old astronomy that should have been replaced by something simpler. But the parsec persists because it emerges naturally from the measurement process. When astronomers measure a star's parallax, they obtain a number in arcseconds. To convert this into a distance, they divide 1 by the parallax. If the parallax is 1 arcsecond, the distance is 1 parsec. If the parallax is half an arcsecond, the distance is 2 parsecs. The math is trivial, and the unit directly reflects the observable quantity. Light years, by contrast, require additional conversion. Measuring parallax gives an angle, not a time. To convert the angle into light years requires calculating the distance in parsecs first, then multiplying by 3.26. The extra step adds nothing useful. It simply converts one unit into another without changing the underlying information. For working astronomers, The parsec is the natural choice because it minimizes conversion and keeps the mathematics simple. The fact that it confuses non-astronomers is beside the point. The parsec exists to serve the needs of measurement, not to communicate with the public. The arcsecond itself requires explanation because it represents a division of angular measurement that most people never encounter in daily life. Angles are typically measured in degrees, a system inherited from ancient Babylonian astronomy. A full circle contains 360 degrees, a number chosen for its mathematical convenience. 360 is divisible by many small integers, which makes it easy to divide a circle into halves, thirds, quarters, sixths, and other simple fractions. Each degree is further divided into 60 arc minutes, and each arc minute is divided into 60 arc seconds. The system is sexagesimal, based on 60 rather than 10, and it predates the metric system by thousands of years. 1 arc second, then, is 1/60th of 1/60th of 1 degree. It is a tiny slice of a circle, so small that it challenges the limits of mechanical precision and optical resolution. To visualize this scale, consider that the full moon spans about half a degree, or 30 arc minutes, or 1800 arc seconds. A single arc second is roughly 1/1800th the width of the moon. It is the apparent size of a quarter, viewed from a distance of 3 miles. It is smaller than the angular resolution of the human eye, which is about 1 arc minute under ideal conditions, meaning the eye cannot distinguish details smaller than 60 arc seconds. Even the best ground-based telescopes, limited by atmospheric turbulence, struggle to resolve features smaller than 1 arc second. The choice of 1 arc second as the defining angle for the parsec was not arbitrary. It reflects the practical limits of 19th century astronomy when the first successful parallax measurements were made. At that time, measuring angles to an accuracy of 1 arc second was at the cutting edge of observational capability. Stars closer than 1 parsec would have parallax angles larger than 1 arc second, making them easier to measure. Stars farther than 1 parsec would have smaller parallax angles, making them progressively harder to measure. The parsec thus represents a natural threshold, the distance at which parallax measurement transitions from difficult to extremely difficult. No star is closer than 1 parsec. The nearest star system, Alpha Centauri, lies at a distance of about 1.3 parsecs, giving it a parallax of roughly 3/4 of an arc second. This is large by stellar standards, but still requires precise instruments to measure. Sirius, the brightest star in the night sky, is about 2.6 parsecs away, with a parallax of roughly 0.38 arc seconds. Beyond 10 parsecs, parallax angles drop below 1/10 of an arc second, pushing the limits of what ground-based telescopes can measure reliably. Beyond 100 parsecs, parallax becomes virtually undetectable from Earth's surface, and distances must be determined by other methods. The inverse relationship between parallax and distance means that small errors in measuring parallax translate into large errors in distance, especially for distant stars. If a star's parallax is measured as 0.1 arc seconds, with an uncertainty of 0.01 arc seconds, the distance is 10 parsecs, with an uncertainty that could place the star anywhere between 9 and 11 parsecs. That is a 20% error, which might seem acceptable. But if the parallax is measured as 0.01 arc seconds, with the same absolute uncertainty of 0.01 arc seconds, the distance could be anywhere from infinity down to 50 parsecs. The percentage error becomes enormous, and the distance measurement becomes almost meaningless. This is why parallax is only useful for nearby stars. The method is geometrically sound, requiring no assumptions about the nature of stars or the properties of light. It is a direct measurement in the sense that it relies only on angles and the known size of Earth's orbit. But it is limited by observational precision, and that precision degrades rapidly with distance. At some point, the parallax angle becomes so small that it cannot be distinguished from zero with any confidence, and at that point parallax ceases to be a useful tool. The baseline for parallax measurement is fixed by Earth's orbit. The distance from Earth to the Sun, 1 astronomical unit, is the longest baseline available without leaving Earth's vicinity entirely. Some proposals have suggested using spacecraft placed at greater distances from the Sun to create longer baselines, but the practical difficulties are immense. A spacecraft twice as far from the Sun as Earth would double the baseline, and thus double the measurable parallax for any given star. This would extend the range of parallax measurements by a factor of 2, but it would also require maintaining precise knowledge of the spacecraft's position over periods of months or years as it observed stars from its distant vantage point. The technical challenges and expense have so far kept such missions in the realm of proposals rather than reality. Instead, astronomers are focused on improving the precision with which angles can be measured from Earth's orbit. The history of parallax measurement is a history of incremental improvements in angular resolution, each improvement extending the range of distances that could be reliably measured. Early telescopes were limited by the quality of their lenses and mirrors, by the stability of their mountings, and by the turbulence of Earth's atmosphere. Even under perfect conditions, air currents and temperature variations cause starlight to shimmer and dance, blurring images and making precise angle measurements difficult. Astronomers refer to this effect as seeing, and on most nights, even at the best observing sites, seeing limits angular resolution to about 1 arcsecond or worse. The development of photography in the 19th century provided a way to record star positions permanently, allowing measurements to be made at leisure rather than in real time at the telescope. Photographic plates could be compared side by side, with images taken months or years apart, and the shifts in star positions could be measured with precision, approaching 1/10 of an arcsecond. This extended the range of parallax measurements to stars several parsecs away, but it did not overcome the fundamental limit imposed by atmospheric turbulence. The real breakthrough came with space-based observations. A telescope placed above Earth's atmosphere is free from the distortions caused by air, and it can measure angles with precision limited only by the quality of its optics and the stability of its platform. The first major space mission dedicated to measuring stellar parallax was Hipparcos, launched in 1989. Over 4 years, Hipparcos measured the parallax of more than 100,000 stars with an accuracy of about 1,000th of an arcsecond. This extended the range of reliable parallax measurements to stars several hundred parsecs away, a 100-fold improvement over ground-based observations. The successor to Hipparcos is Gaia, launched in 2013. Gaia measures stellar positions with an accuracy of a few millionths of an arcsecond for the brightest stars and a few tens of millionths of an arcsecond for fainter stars. This extraordinary precision extends the range of parallax measurements to stars thousands of parsecs away, though with increasing uncertainty as distance increases. Gaia has measured parallax for more than 1 billion stars, providing a 3-dimensional map of the Milky Way galaxy with unprecedented detail. The parsec, once a unit defined by the practical limits of 19th century telescopes, has become the natural unit for describing the structure of the galaxy itself. Earth's orbit provides the baseline for parallax measurement, but the orbit itself had to be understood before parallax could be used to measure stellar distances. The distance from Earth to the Sun, now called the astronomical unit, was not accurately known until the 18th century. Early estimates varied wildly, with some ancient astronomers placing the Sun only a few million miles away, and others suggesting distances 10 times larger. The true value, about 93 million miles, was not established with confidence until observations of Venus transiting across the face of the Sun provided a way to triangulate the Sun's distance using geometry. The method relied on observing the transit from widely separated locations on Earth. Observers at different latitudes would see Venus cross the Sun along slightly different paths, and the difference in those paths could be used to calculate the distance to Venus. Once the distance to Venus was known, the distances to the Sun and other planets could be determined using Kepler's laws of planetary motion, which relate orbital periods to orbital sizes. The result was a value for the astronomical unit accurate to within a few percent, good enough to serve as the baseline for parallax measurements. The importance of knowing this baseline cannot be overstated. The parsec is defined in terms of the astronomical unit. 1 parsec is the distance at which an object has a parallax of 1 arcsecond when viewed from opposite sides of Earth's orbit, and Earth's orbit has a radius of 1 astronomical unit. If the astronomical unit were different, the parsec would be different. The 2 units are linked by definition, and any error in the astronomical unit translates directly into an error in distances measured in parsecs. Modern measurements of the astronomical unit use radar ranging to Venus and Mars. Radio signals are transmitted from Earth, bounce off the surface of the planet and return to Earth. The time delay between transmission and reception gives the round-trip light travel time, and multiplying by the speed of light gives twice the distance to the planet. These measurements are accurate to within a few meters, making the astronomical unit one of the most precisely known distances in astronomy. The current accepted value is about 149,597,870 kilometers, or roughly 93 million miles. This precision in the baseline allows parallax measurements to be converted into absolute distances with confidence. When Gaia measures a parallax of 1 arcsecond for a hypothetical star, astronomers know the star is exactly 1 parsec away, not approximately 1 parsec. The uncertainty in the distance comes from the uncertainty in measuring the parallax angle, not from uncertainty in the baseline. This separation of errors is important because it means improvements in measuring parallax directly translate into improvements in measuring distance, without requiring better knowledge of Earth's orbit. The shape of Earth's orbit also matters. The orbit is not a perfect circle but an ellipse, with the Sun at one focus. The distance from Earth to the Sun varies over the course of a year, ranging from about 91 million miles at perihelion in early January to about 94.5 million miles at aphelion in early July. This variation is small, only about 3%, but it affects parallax measurements because the baseline changes depending on when observations are made. Astronomers account for this by using the semi-major axis of Earth's orbit, the average of the perihelion and aphelion distances, as the standard baseline. This value, 1 astronomical unit, represents the mean distance from Earth to the Sun over a complete orbit. The timing of observations also matters. Parallax is largest when Earth is at maximum displacement from the Sun relative to the star being observed. For a star lying in the plane of Earth's orbit, maximum displacement occurs when Earth is 90 degrees ahead of or behind the position where the line from the Sun to the star intersects Earth's orbit. For stars not in the orbital plane, the geometry is more complicated, but the principle remains the same. The optimal time to observe a star for a parallax measurement is when Earth's motion carries it perpendicular to the line of sight to the star, maximizing the change in viewing angle. In practice, astronomers observe stars continuously over a full year or longer, recording positions at many points along Earth's orbit. This provides multiple measurements of the parallax effect, allowing errors to be averaged out and systematic biases to be identified and corrected. A star's apparent position traces out a small ellipse on the sky over the course of a year, with the size and orientation of the ellipse determined by the star's parallax and its location relative to Earth's orbital plane. Measuring this ellipse and fitting it to the expected pattern gives both a parallax and a measure of how reliable the parallax measurement is. The motion of the Sun itself complicates matters further. The Sun is not stationary in space but orbits the centre of the Milky Way galaxy at a speed of about 500,000 miles per hour. Over the course of a year, the Sun moves through space by a distance comparable to the size of Earth's orbit, carrying Earth along with it. This motion creates an additional parallax effect for nearby stars, called secular parallax, which is distinct from the annual parallax caused by Earth's orbit. Secular parallax is useful for measuring distances to stars too far away for annual parallax to be detected, but it requires knowing the Sun's velocity through space with precision and waiting years or decades for the effect to accumulate. The relationship between Earth's orbit and stellar parallax highlights a fundamental principle of distance measurement in astronomy. Every method relies on some known scale, some reference distance or reference object that serves as the foundation for further measurements. For parallax, the reference is Earth's orbit. The astronomical unit is the measuring stick, and everything else is scaled relative to it. Without precise knowledge of the astronomical unit, parallax measurements would give only relative distances, telling us which stars are closer and which are farther, but not providing absolute distances in miles or kilometers or any other unit. This dependence on a reference scale extends throughout astronomy. Beyond the range of parallax, other methods take over, and each of those methods must be calibrated using parallax measurements of nearby stars. The entire edifice of cosmic distance measurement rests on the foundation of parallax, and parallax rests on the foundation of Earth's orbit. If the astronomical unit were wrong, every distance in the universe would be wrong by the same factor. The fact that distances measured by different methods agree with each other, at least within the uncertainties of measurement, suggests that the astronomical unit is indeed known accurately, and that the parallax method is sound. The parsec, then, is not just a unit of distance. It is a unit that encodes the geometry of Earth's orbit and the precision with which astronomers can measure angles. It is a unit that emerges from the measurement process itself, rather than being imposed from outside, and it is a unit that connects the human scale of Earth's orbit to the cosmic scale of interstellar space, bridging the gap between what we can directly experience and what we can only infer through geometry and calculation. Triangulation is not unique to astronomy. Surveyors use the same principle to map terrain, measuring angles from known positions to determine the locations of distant landmarks. The method is ancient, dating back at least to Greek mathematics, and it remains one of the most reliable ways to measure distances that cannot be traversed directly. The key insight is that a triangle is fully determined by one side and two angles, or by two sides and one angle. If you know the length of one side and can measure the angles at two corners, you can calculate the lengths of the other sides using trigonometry. In surveying, the known side is called the baseline. It might be a measured distance between two survey markers, established with care using chains or rods or laser rangefinders. From each end of the baseline, surveyors measure the angle to a distant point, perhaps a mountaintop or a building. These two angles, combined with the known length of the baseline, define a triangle. The distance from either end of the baseline to the distant point can be calculated using the sine rule or other trigonometric identities. The method is straightforward and does not require travelling to the distant point or making any assumptions about its properties. Stellar parallax is triangulation on a cosmic scale. The baseline is the diameter of Earth's orbit, 186 million miles. The distant point is a star, perhaps trillions of miles away. The angles are measured not from two fixed survey markers, but from Earth's position at two different times, 6 months apart. The principle is identical to terrestrial surveying, but the scale is vastly different. The baseline is millions of times longer, and the angles are millions of times smaller. Yet the mathematics is the same, and the method is just as reliable, limited only by the precision with which angles can be measured. The reason parallax works for stars is that stars are effectively point sources of light. They have physical size, of course, but they are so far away that even the largest telescopes cannot resolve their disks. A star appears as a point, and its position can be measured with precision limited only by the quality of the instrument and the steadiness of the atmosphere. This is fortunate because if stars had measurable sizes, parallax would be more complicated. The parallax would vary depending on which part of the star's surface was being observed, and disentangling the star's size from its distance would require additional information. The geometry of stellar parallax can be understood by imagining the view from the star looking back at Earth. From the star's perspective, Earth and the Sun orbit their common centre of mass, which lies very close to the Sun's centre because the Sun is so much more massive than Earth. As Earth moves around its orbit, an observer on the star would see Earth trace out a small ellipse with the Sun at one focus. The angular size of this ellipse as seen from the star is twice the parallax angle. If the parallax is 1 arcsecond, the ellipse spans 2 arcseconds from edge to edge. This is an extraordinarily small angle, but it is measurable, and it provides a direct geometric link between the star's distance and something observable from Earth. The elegance of parallax lies in its simplicity. It requires no assumptions about the nature of the star, no knowledge of its temperature or composition or intrinsic brightness. It does not depend on the properties of light or the behaviour of space-time. It is pure geometry, a consequence of viewing an object from two different positions. This makes parallax a primary distance indicator, a method that stands on its own without needing calibration from other techniques. Every other method of measuring cosmic distance, with very few exceptions, relies on parallax for calibration. The limitations of parallax are also geometric. The parallax angle decreases in proportion to distance, double the distance, and the parallax is halved. This means that at large distances the parallax becomes too small to measure and the method fails. The failure is not sudden, but gradual. As distance increases, the uncertainty in the parallax measurement grows relative to the parallax itself, and eventually the uncertainty becomes larger than the measurement. At that point, the distance is essentially unknown. We can say the star is farther than some minimum distance, but we cannot say how much farther. For ground-based telescopes, this limit is reached at a few tens of parsecs. Atmospheric turbulence limits angular resolution to about 1 arcsecond under good conditions, and measuring parallax requires detecting shifts much smaller than the resolution limit. This can be done by averaging many observations and using statistical techniques to extract the parallax signal from the noise, but there are practical limits. Beyond about 50 parsecs, the parallax is smaller than 0.02 arcseconds, and ground-based measurements become unreliable. Space-based telescopes push this limit much farther. Hipparcos, with its millisecond precision, could measure parallax reliably, out to a few hundred parsecs. Gaia, with microarcsecond precision, extends the range to several thousand parsecs, encompassing a significant fraction of the Milky Way galaxy. But even Gaia has limits. The galaxy is roughly 30,000 parsecs across, and most of it lies beyond the range of direct parallax measurement. For the majority of stars in the Milky Way, and for all stars in other galaxies, parallax provides no information, and distances must be inferred by other means. The transition from parallax to other methods marks a critical point in the cosmic distance scale. Within the range of parallax, distances are known with precision and confidence. Beyond that range, distances become progressively more uncertain, dependent on assumptions and calibrations that introduce additional sources of error. This is not a failure of astronomy, but a consequence of the vast scales involved. The universe is so large that no single method can span the full range of distances from nearby stars to the most distant galaxies. Instead, astronomers use a ladder of techniques, each one calibrated by the previous one, extending the reach of measurement step by step. Parallax forms the bottom rung of this ladder. It is the foundation on which everything else is built. If the parallax measurements are wrong, every subsequent distance is wrong. If the parallax measurements are uncertain, that uncertainty propagates through every later step. This is why astronomers invest so much effort in measuring parallax with the highest possible precision. The better the parallax measurements, the more reliable the entire cosmic distance scale becomes, and the more reliable the distance scale, the better we can understand the structure and evolution of the universe. The parsec, as the natural unit of parallax-based distances, becomes the natural unit for discussing the structure of the galaxy. Stars within a few parsecs of the Sun are neighbours by galactic standards. Stars within a few hundred parsecs are nearby, part of the local neighbourhood. Stars within a few thousand parsecs are still within the local region of the galaxy, the spiral arm that contains the Sun. Beyond that, distances are measured in kiloparsecs, thousands of parsecs, a scale that spans the galaxy itself. The galactic centre lies about 8 kiloparsecs from the Sun. The edge of the galactic disk extends to about 15 kiloparsecs. These distances are so large that parallax cannot measure them directly, but they are still expressed in parsecs because the parsec has become the standard unit of galactic astronomy. The first successful measurement of stellar parallax came in the 1830s, more than 2 centuries after Galileo turned a telescope toward the heavens. The delay was not due to lack of trying. Astronomers had been searching for parallax since the time of Copernicus, knowing that if Earth truly orbited the Sun, nearby stars should exhibit measurable shifts in position over the course of a year. The failure to detect these shifts was used by critics of the heliocentric model as evidence that Earth was stationary. Copernicus and his followers argued that the stars were simply too far away for their parallax to be visible, but without direct evidence the argument remained speculative. By the early 19th century, telescopes had improved to the point where measuring angles to within 1 arcsecond was possible under good conditions. Several astronomers began systematic programs to search for stellar parallax, focusing on stars that seemed most likely to be nearby. The logic was straightforward. Nearby stars should have larger parallax than distant stars, and nearby stars might be identifiable by their brightness or by their motion across the sky. Stars with large, proper motion, meaning they change position relative to other stars over periods of years or decades, were thought to be closer because their motion would be more apparent at shorter distances. The first confirmed detection came almost simultaneously from 3 astronomers working independently. Friedrich Bessel in Germany focused on the star 61 Cygni, a faint star with large proper motion. Thomas Henderson in South Africa observed Alpha Centauri, the brightest star in the constellation Centaurus. Friedrich von Struve in Russia measured Vega, one of the brightest stars in the northern sky. All 3 detected parallax, though their results were not announced simultaneously. Henderson made his observations first but delayed publishing his results. Bessel published first in 1838, reporting a parallax of about 0.31 arcseconds for 61 Cygni, corresponding to a distance of roughly 3 parsecs. The achievement was monumental, not because it revealed anything unexpected about the stars themselves, but because it confirmed what astronomers had long suspected. The stars were incomprehensibly distant. 61 Cygni at 3 parsecs was about 20 trillion miles away, more than 500,000 times the distance from Earth to the Sun. Alpha Centauri, closer at 1.3 parsecs, was still so remote that light took more than 4 years to reach Earth. These were distances that defied human intuition, distances so large that no existing unit of measurement seemed adequate to express them. The discovery of stellar parallax also validated the heliocentric model in a way that earlier arguments could not. Skeptics had pointed to the absence of detectable parallax as a problem for the idea that Earth moved. Now parallax had been detected, and its size confirmed that Earth did indeed orbit the Sun. The smallness of the parallax explained why it had taken so long to measure. The stars were not attached to a sphere a short distance beyond the planets, as ancient models suggested. They were scattered through space at distances that varied enormously, with even the nearest stars lying at distances thousands of times greater than the span of the solar system. The early parallax measurements were painstaking. Bessel's work on 61 Cygni required observations spread over more than a year, with careful attention to systematic errors and instrumental effects. Telescopes at the time were subject to flexure, changes in shape caused by temperature variations and the weight of the instrument itself. Atmospheric refraction bent starlight as it passed through the air, and the amount of bending depended on the star's altitude above the horizon. Even the rotation of Earth introduced complications, as the direction of gravity changed slightly depending on the time of night. All of these effects had to be understood and corrected before reliable parallax measurements could be made. Bessel's success depended on choosing the right target. 61 Cygni was not a bright star, but it had the largest proper motion of any star known at the time, moving about 5 arcseconds per year across the sky. This suggested it was nearby, and indeed it proved to be one of the closest stars visible from northern latitudes. By focusing on a nearby star, Bessel maximized the parallax signal he was trying to detect, giving himself the best chance of success. Had he chosen a more distant star, even with a better telescope, he might not have detected parallax at all. Henderson's observations of Alpha Centauri were made during his tenure as director of the Royal Observatory at the Cape of Good Hope in South Africa. Alpha Centauri is a bright star visible only from southern latitudes, and it too exhibits substantial proper motion. Henderson measured its position relative to nearby stars over the course of a year and detected a parallax of about 3/4 of an arcsecond, consistent with a distance of 1.3 parsecs. He did not immediately publish his results, apparently doubting their accuracy, and by the time his work appeared in print, Bessel had already announced his measurement of 61 Cygni. Struve's measurement of Vega was less accurate than Bessel's or Henderson's, partly because Vega is more distant, at about 7.5 parsecs, giving it a much smaller parallax. Struve reported a value of about 0.1 arcseconds, which was in the right range but carried large uncertainties. Later measurements refined this value, but Struve's work was important because it demonstrated that parallax could be measured for bright stars as well as faint ones, and that proper motion was not the only indicator of proximity. These early successes opened the door to measuring distances for dozens, then hundreds, then thousands of stars. Each measurement added a new point to the emerging three-dimensional map of the stellar neighbourhood. Some stars, previously thought to be nearby based on their brightness, turned out to be distant and intrinsically luminous. Others, faint and easily overlooked, proved to be close neighbours of the Sun. The data began to reveal patterns. Bright blue stars were generally distant and luminous. Dim red stars were often nearby but intrinsically faint. The Sun itself appeared to be intermediate, neither exceptionally bright nor exceptionally dim, neither very close to other stars nor isolated in a void. The distribution of stars in space also became apparent. Stars were not uniformly scattered but showed clustering and structure, with some regions more densely populated than others. The Milky Way, long recognized as a band of light encircling the sky, resolved into a flattened disk of stars when viewed in 3 dimensions. The Sun lay within this disk, not at its centre but offset by a considerable distance. The structure suggested that stars formed groups, and that these groups had histories, origins, and perhaps even ages that could be inferred from their properties. The parsec emerged as the natural unit for describing these discoveries because it matched the scale of the measurements. Stars within 1 parsec were extraordinarily rare. Only a few such stars existed, and most were faint red dwarfs barely visible even through telescopes. Stars within 10 parsecs were more common, but still numbered only in the dozens. The majority of stars within this volume were cooler and fainter than the Sun, a pattern that would become clearer as more parallax measurements accumulated. The galaxy was not filled with stars like the Sun, but with stars less massive, less luminous, and longer lived, a finding that reshaped understanding of stellar populations and galactic structure. The light year predates the parsec as a unit of astronomical distance, and for much of the public, it remains the more intuitive choice. The concept is straightforward. Light travels at a fixed speed, approximately 186,000 miles per second, and a light year is the distance light covers in 1 year. This comes to about 6 trillion miles, a number that is incomprehensibly large but at least based on a familiar idea. Light travels, time passes, distance accumulates. The logic is linear and easy to follow. The parsec, by contrast, seems unnecessarily abstract. It is defined by an angle, measured from a baseline determined by Earth's orbit, and it corresponds to a distance only through trigonometric calculation. For someone encountering the term for the first time, the definition raises more questions than it answers. Why use an angle to define a distance? Why 1 arcsecond specifically? Why not simply measure everything in light years and avoid the confusion? The answers to these questions lie in the practicalities of astronomical measurement, but those practicalities are not immediately obvious to anyone outside the field. The parsec exists because it simplifies the relationship between what astronomers observe and what they want to know. When a star's parallax is measured, the result is an angle in arcseconds. To find the distance in parsecs, you divide one by the parallax. If the parallax is 0.5 arcseconds, the distance is 2 parsecs. If the parallax is 0.1 arcseconds, the distance is 10 parsecs. The calculation is trivial, requiring only division, and the result is in a unit that directly reflects the precision of the measurement. A parallax measured to 3 decimal places gives a distance in parsecs to similar precision. Converting parallax to light years adds an unnecessary step. First, the parallax must be converted to parsecs using the division described above. Then, the distance in parsecs must be multiplied by 3.26 to get light years. The extra multiplication does not improve the accuracy or provide additional information. It simply changes the units. For astronomers who work with parallax measurements routinely, performing this extra step hundreds or thousands of times serves no purpose. The parsec is the natural unit because it emerges directly from the measurement process. The mathematical relationship is even simpler when expressed algebraically. If the parallax is denoted by the letter p, measured in arcseconds, and the distance is denoted by the letter d, measured in parsecs, then the relationship is d equals 1 divided by p. This inverse relationship is fundamental to parallax geometry. It also means that the uncertainty in the parallax translates directly into uncertainty in the distance, and that uncertainty grows rapidly as the parallax becomes smaller. A 10% error in measuring a large parallax gives roughly a 10% error in distance. A 10% error in measuring a small parallax can give a much larger percentage error in distance, because the division amplifies uncertainties when the denominator is small. The light year, while more intuitive in some respects, obscures this relationship. The conversion from parallax to light years involves multiplying 1 over the parallax by 3.26, which combines the geometric inversion with an arbitrary conversion factor. The result is a distance that no longer has a simple mathematical connection to the observable quantity. For working astronomers, this is a disadvantage. The parsec keeps the mathematics transparent, making it easier to assess measurement quality and propagate uncertainties through calculations. There is also a historical dimension to the choice of units. The parsec was defined in the early 20th century, after parallax measurements had become routine but before light years were widely adopted. The term itself is a contraction of parallax and arcsecond, making its origin explicit. Astronomers at the time were focused on building a distance scale for the galaxy, and they needed a unit that matched the scale of their measurements. The parsec fit naturally because it was comparable to the distances being measured. Most nearby stars lay within a few parsecs, and the structure of the local stellar neighbourhood could be described in terms of tens or hundreds of parsecs. The light year, by contrast, gained prominence through popular science writing and science fiction. It is easier to explain to a general audience because it relies on the concept of light travel time, which is more familiar than parallax geometry. Science fiction writers adopted the light year because it provided a comprehensible way to describe interstellar distances, even if those distances were still far beyond human reach. The parsec, mentioned less often in popular contexts, remained the domain of professional astronomy. This divergence between professional and popular usage has created lasting confusion. Astronomy textbooks written for students use parsecs almost exclusively when discussing parallax and the distance scale. Popular articles and documentaries often convert distances to light years to make them more accessible. The result is that people learning about astronomy encounter both units, sometimes in the same paragraph, without a clear explanation of why both exist or when each is appropriate. The situation is compounded by the fact that neither unit corresponds to any human scale of experience. Both are so large that they might as well be infinite from the perspective of everyday life. Some argue that the parsec should be abandoned in favour of light years for the sake of clarity, but this misses the point. The parsec is not a pedagogical choice intended to make astronomy easier to understand. It is a working unit chosen because it simplifies the mathematics of distance measurement. Replacing it with light years would not eliminate the underlying complexity. It would simply hide that complexity behind a conversion factor, making the relationship between observation and distance less transparent rather than more so. The debate over units also extends to larger scales. Beyond the immediate neighbourhood of the Sun, distances are often expressed in kiloparsecs, thousands of parsecs or megaparsecs, millions of parsecs. The centre of the Milky Way lies about 8 kiloparsecs away. The Andromeda Galaxy, the nearest large galaxy to the Milky Way, is about 770 kiloparsecs distant. Galaxy clusters can be separated by tens or hundreds of megaparsecs. At these scales, the choice between parsecs and light years becomes even more arbitrary. A kiloparsec is about 3,260 light years. A megaparsec is about 3.26 million light years. The numbers are different, but the underlying distances are the same. Cosmologists who study the universe on the larger scales often prefer megaparsecs because the unit is convenient for expressing the distances between galaxies and galaxy clusters. Quoting these distances in light years would require using numbers in the millions or billions, which are cumbersome to write and difficult to compare. Megaparsecs keep the numbers manageable, typically ranging from single digits to a few thousand. This is the same logic that leads astronomers to use parsecs for stellar distances. The unit is chosen to match the scale of the phenomena being studied, not to conform to some external standard of clarity or simplicity. The persistence of the parsec, despite its opacity to non-astronomers, reflects a broader principle in science. Units are tools, and like any tool, they are chosen for their utility in specific contexts. The meter is convenient for measuring room dimensions, but awkward for expressing atomic distances. The kilogram is useful for weighing groceries, but impractical for describing planetary masses. Every field develops its own system of units tailored to the problems it addresses, and astronomy is no exception. The parsec is astronomy's unit, defined by astronomers for astronomy, and it remains in use because it serves its purpose better than any alternative. The light year predates the parsec as a unit of astronomical distance, and for much of the public it remains the more intuitive choice. The concept is straightforward. Light travels at a fixed speed, approximately 186,000 miles per second, and a light year is the distance light covers in 1 year. This comes to about 6 trillion miles, a number that is incomprehensibly large but at least based on a familiar idea. Light travels, time passes, distance accumulates. The logic is linear and easy to follow. The parsec, by contrast, seems unnecessarily abstract. It is defined by an angle, measured from a baseline determined by Earth's orbit, and it corresponds to a distance only through trigonometric calculation. For someone encountering the term for the first time, the definition raises more questions than it answers. Why use an angle to define a distance? Why 1 arcsecond specifically? Why not simply measure everything in light years and avoid the confusion? The answers to these questions lie in the practicalities of astronomical measurement. but those practicalities are not immediately obvious to anyone outside the field. The parsec exists because it simplifies the relationship between what astronomers observe and what they want to know. When a star's parallax is measured, the result is an angle in arc seconds. To find the distance in parsecs, you divide 1 by the parallax. If the parallax is 0.5 arcseconds, the distance is 2 parsecs. If the parallax is 0.1 arcseconds, the distance is 10 parsecs. The calculation is trivial, requiring only division, and the result is in a unit that directly reflects the precision of the measurement. A parallax measured to 3 decimal places gives a distance in parsecs to similar precision. Converting parallax to light years adds an unnecessary step. First, the parallax must be converted to parsecs using the division described above. Then the distance in parsecs must be multiplied by 3.26 to get light years. The extra multiplication does not improve the accuracy or provide additional information, it simply changes the units. For astronomers who work with parallax measurements routinely, performing this extra step hundreds or thousands of times serves no purpose. The parsec is the natural unit because it emerges directly from the measurement process. The mathematical relationship is even simpler when expressed algebraically. If the parallax is denoted by the letter p, measured in arcseconds, and the distance is denoted by the letter d, measured in parsecs, then the relationship is d equals 1 divided by p. This inverse relationship is fundamental to parallax geometry. It also means that the uncertainty in the parallax translates directly into uncertainty in the distance, and that uncertainty grows rapidly as the parallax becomes smaller. A 10% error in measuring a large parallax gives roughly a 10% error in distance. A 10% error in measuring a small parallax can give a much larger percentage error in distance, because the division amplifies uncertainties when the denominator is small. The light year, while more intuitive in some respects, obscures this relationship. The conversion from parallax to light years involves multiplying 1 over the parallax by 3.26, which combines the geometric inversion with an arbitrary conversion factor. The result is a distance that no longer has a simple mathematical connection to the observable quantity. For working astronomers, this is a disadvantage. The parsec keeps the mathematics transparent, making it easier to assess measurement quality and propagate uncertainties through calculations. There is also a historical dimension to the choice of units. The parsec was defined in the early 20th century, after parallax measurements had become routine but before light years were widely adopted. The term itself is a contraction of parallax and arcsecond, making its origin explicit. Astronomers at the time were focused on building a distance scale for the galaxy, and they needed a unit that matched the scale of their measurements. The parsec fit naturally because it was comparable to the distances being measured. Most nearby stars lay within a few parsecs, and the structure of the local stellar neighbourhood could be described in terms of tens or hundreds of parsecs. The light year, by contrast, gained prominence through popular science writing and science fiction. It is easier to explain to a general audience because it relies on the concept of light travel time, which is more familiar than parallax geometry. Science fiction writers adopted the light year because it provided a comprehensible way to describe interstellar distances, even if those distances were still far beyond human reach. The parsec, mentioned less often in popular contexts, remained the domain of professional astronomy. This divergence between professional and popular usage has created lasting confusion. Astronomy textbooks written for students use parsecs almost exclusively when discussing parallax and the distance scale. Popular articles and documentaries often convert distances to light years to make them more accessible. The result is that people learning about astronomy encounter both units, sometimes in the same paragraph, without a clear explanation of why both exist or when each is appropriate. The situation is compounded by the fact that neither unit corresponds to any human scale of experience. Both are so large that they might as well be infinite from the perspective of everyday life. Some argue that the parsec should be abandoned in favour of light years for the sake of clarity, but this misses the point. The parsec is not a pedagogical choice intended to make astronomy easier to understand. It is a working unit chosen because it simplifies the mathematics of distance measurement. Replacing it with light years would not eliminate the underlying complexity. It would simply hide that complexity behind a conversion factor, making the relationship between observation and distance less transparent rather than more so. The debate over units also extends to larger scales. Beyond the immediate neighbourhood of the Sun, distances are often expressed in kiloparsecs, thousands of parsecs, or megaparsecs, millions of parsecs. The centre of the Milky Way lies about 8 kiloparsecs away. The Andromeda Galaxy, the nearest large galaxy to the Milky Way, is about 770 kiloparsecs distant. Galaxy clusters can be separated by tens or hundreds of megaparsecs. At these scales, the choice between parsecs and light years becomes even more arbitrary. A kiloparsec is about 3,260 light years. A megaparsec is about 3.26 million light years. The numbers are different, but the underlying distances are the same. Cosmologists who study the universe on the largest scales often prefer megaparsecs because the unit is convenient for expressing the distances between galaxies and galaxy clusters. Quoting these distances in light years would require using numbers in the millions or billions, which are cumbersome to write and difficult to compare. Megaparsecs keep the numbers manageable, typically ranging from single digits to a few thousand. This is the same logic that leads astronomers to use parsecs for stellar distances. The unit is chosen to match the scale of the phenomena being studied, not to conform to some external standard of clarity or simplicity. The persistence of the parsec, despite its opacity to non-astronomers, reflects a broader principle in science. Units are tools, and like any tool, they are chosen for their utility in specific contexts. The meter is convenient for measuring room dimensions, but awkward for expressing atomic distances. The kilogram is useful for weighing groceries, but impractical for describing planetary masses. Every field develops its own system of units tailored to the problems it addresses, and astronomy is no exception. The parsec is astronomy's unit, defined by astronomers for astronomy, and it remains in use because it serves its purpose better than any alternative. The mathematical elegance of the parsec becomes most apparent when examining the formula that relates parallax to distance. The relationship is not merely convenient, but inevitable, given the geometry of the situation. Consider a right triangle where one leg is the radius of Earth's orbit, measured in astronomical units, and the opposite angle is the parallax angle measured in arcseconds. The distance to the star forms the hypotenuse of this triangle. For small angles, which is always the case with stellar parallax, the tangent of the angle is approximately equal to the angle itself when measured in radians. Converting 1 arcsecond to radians gives approximately 0.00004848 radians. The radius of Earth's orbit is 1 astronomical unit. Dividing 1 astronomical unit by this value in radians gives the distance corresponding to a parallax of 1 arcsecond, which is by definition 1 parsec. The calculation establishes the parsec as a natural consequence of the geometry, not an arbitrary choice. Any other definition would introduce unnecessary conversion factors into the basic parallax equation. The inverse relationship between parallax and distance also has important implications for how distance errors behave. When parallax is large, meaning the star is nearby, the distance is small and well determined. When parallax is small, meaning the star is distant, the distance becomes increasingly uncertain. This is not just a matter of measurement precision, but a fundamental property of the inverse relationship. The derivative of 1 over p with respect to p is negative 1 over p squared, which means small changes in p produce changes in distance that grow quadratically as p decreases. In practical terms, this means that a star with a parallax of 1 arcsecond, measured with an uncertainty of 0.01 arcseconds, has a distance of 1 parsec, with an uncertainty of about 0.01 parsecs, roughly 1%. A star with a parallax of 0.1 arcseconds, and the same absolute uncertainty of 0.01 arcseconds has a distance of 10 parsecs, but the uncertainty is now about 1 parsec, 10% of the distance. A star with a parallax of 0.01 arcseconds and the same uncertainty has a distance of 100 parsecs, but the uncertainty is now 10 parsecs or more, making the distance barely useful. This behaviour places a natural limit on the range of parallax measurements. Even with perfect instruments, there is a point beyond which parallax becomes too small to distinguish from zero with any confidence. For Gaia, which measures parallax with an uncertainty of about 0.02 milliseconds for bright stars, the effective range is roughly 5,000 parsecs for the most favourable cases. Beyond this distance, the parallax is smaller than the measurement uncertainty, and the distance cannot be reliably determined. For most stars, the practical limit is closer to 1,000 parsecs. The inverse relationship also explains why astronomers use the reciprocal of distance, called absolute parallax in some contexts. Instead of working with distance directly, they work with 1 over distance, which is proportional to the parallax. This simplifies certain calculations because the quantity being manipulated is closer to what is actually measured. In statistical studies of stellar populations, for example, it is often more appropriate to analyse parallaxes rather than distances, because parallaxes are the direct observables, and distances are derived quantities that carry nonlinear uncertainties. The symmetry of the parsec definition extends to other aspects of parallax measurement. A star at 2 parsecs has a parallax of 0.5 arcseconds, exactly half that of a star at 1 parsec. A star at half a parsec would have a parallax of 2 arcseconds, twice as large. The relationship is perfectly reciprocal, and this reciprocity makes mental arithmetic straightforward. Astronomers can convert between parallax and distance without calculators or lookup tables simply by dividing one by the other. This simplicity breaks down when parallax is converted to other units. A star at 1 light-year has a parallax of about 0.307 arcseconds, a number that is not particularly memorable or easy to work with. A star at 10 light-years has a parallax of about 0.0307 arcseconds. The relationship is still inverse, but the conversion factor obscures the elegance. The parsec preserves the one-to-one correspondence between parallax and distance, making the unit indispensable for anyone working directly with parallax data. The definition of the parsec also connects naturally to other astronomical quantities. The absolute magnitude of a star, a measure of its intrinsic brightness, is defined as the apparent magnitude the star would have if it were located at a distance of 10 parsecs. This choice is not arbitrary. 10 parsecs is far enough that most stars are dimmer than their intrinsic brightness, making absolute magnitude a useful standard, but it is close enough that the distance is within the range of parallax measurements for many stars. If absolute magnitude had been defined at 10 light-years instead, the conversion between distance modulus and distance would require additional factors that complicate the mathematics. The distance modulus itself, which relates apparent magnitude to absolute magnitude through distance, is expressed most simply when distance is measured in parsecs. The formula is apparent magnitude minus absolute magnitude equals 5 times the logarithm base 10 of distance in parsecs minus 5. If distance is measured in light-years, the formula requires subtracting a different constant, 5 times the logarithm of 3.26, which equals about 2.56. This interconnection of definitions reveals a deeper truth about scientific units. They are not isolated choices, but parts of a coherent system, where each definition supports the others. The parsec is defined in terms of the astronomical unit, which is defined by the radius of Earth's orbit. The absolute magnitude is defined at 10 parsecs. The distance modulus formula is optimized for distances in parsecs. Changing any one of these definitions would require changing others to maintain consistency, and the result would be no simpler than the current system. The parsec also appears naturally in the study of stellar motions. A star's tangential velocity, the component of its motion perpendicular to the line of sight, can be calculated from its proper motion and distance. Proper motion is measured in arcseconds per year, and distance is measured in parsecs. The tangential velocity in kilometers per second is approximately 4.74 times the proper motion in arcseconds per year times the distance in parsecs. If distance were measured in light-years, the conversion factor would be different and less memorable. The structure of these relationships is not coincidental. Astronomers have constructed a system of units and definitions that work together to minimize the need for conversion factors and to keep common calculations as simple as possible. The parsec sits at the center of this system because it is derived from the most fundamental method of measuring distance, and all other distance-related quantities are defined in terms that assume the parsec as the natural unit. Abandoning the parsec would require redefining not just distances, but also absolute magnitudes, distance moduli, and various kinematic quantities, creating more confusion than clarity. Within 10 parsecs of the Sun, the stellar neighbourhood is sparsely populated but well mapped. Current catalogues list fewer than 500 known stars and brown dwarfs within this volume, though the true number is likely somewhat higher as faint objects continue to be discovered. The distribution is far from uniform. Some regions contain small groups of stars moving together through space, while others appear nearly empty. The nearest star system, Alpha Centauri, lies at 1.3 parsecs and consists of 3 stars, 2 Sun-like stars orbiting each other closely, and a small red dwarf called Proxima Centauri that orbits the pair at a great distance. Proxima Centauri is actually the closest individual star to the Sun, fractionally nearer than the other 2 components of the Alpha Centauri system. Its proximity makes it a target for studies of nearby stellar systems and for speculative discussions of interstellar travel, though the actual distance of about 1.3 parsecs translates to roughly 25 trillion miles, a gap that remains far beyond current technology to cross. The star itself is unremarkable except for its closeness. It is a red dwarf, a class of star so dim that it cannot be seen with the naked eye, despite being the nearest stellar neighbour. Beyond Alpha Centauri, the next nearest stars include Barnard's star at about 1.8 parsecs, Wolf 359 at 2.3 parsecs, and Lalande 21185 at 2.5 parsecs. All of these are red dwarfs, considerably less massive and less luminous than the Sun. In fact, red dwarfs dominate the local stellar population. Of the 50 or so closest stars, roughly 3/4 are red dwarfs, with masses ranging from about 8% to half the mass of the Sun. Their low luminosity means they contribute little to the light we see in the night sky, despite being the most common type of star by number. The few bright stars visible to the naked eye within 10 parsecs are exceptional. Sirius, the brightest star in Earth's night sky, lies at 2.6 parsecs. Its brightness is due partly to proximity and partly to its intrinsic luminosity, which is about 25 times that of the Sun. Sirius is actually a binary system, consisting of a bright main sequence star and a white dwarf companion that orbits it every 50 years. The white dwarf, called Sirius B, was once a much larger star that exhausted its nuclear fuel and collapsed to a dense remnant about the size of Earth. Procyon, another bright star visible from Earth, lies at about 3.5 parsecs. Like Sirius, it is a binary system with a white dwarf companion. The primary star is somewhat larger and more luminous than the Sun, though not as extreme as Sirius. The presence of white dwarf companions in both systems indicates that stellar evolution has already progressed beyond the main sequence stage for some stars in the solar neighbourhood, even though the region is relatively young by galactic standards. The distribution of stellar types within 10 parsecs provides insight into the broader population of the galaxy. If the local neighbourhood is representative, then the vast majority of stars are faint red dwarfs that contribute little to the overall light output. The bright stars that dominate the night sky are rare exceptions, more luminous than typical stars and therefore visible over much greater distances. This creates a selection effect where the stars we see most easily are not representative of the stars that actually exist in greatest number. Parallax measurements within 10 parsecs are relatively straightforward, because the parallax angles are large enough to be measured with high precision even from the ground. A star at 10 parsecs has a parallax of 0.1 arcseconds, well within the capability of modern instruments. Ground-based parallax measurements pioneered in the 19th and early 20th centuries were largely confined to this volume, and even today, the stars within 10 parsecs have the best determined distances in the galaxy. Uncertainties are typically a few percent or less, small enough that the distances can be treated as essentially exact for most purposes. The three-dimensional structure of the local neighbourhood reveals no obvious pattern. Stars are not arranged in a sphere or disk or any other regular geometry. Some regions have higher density than others, but the variations are modest. There are no large voids completely empty of stars, but neither are there dense clusters where stars are packed closely together. The nearest approach between any two stars in the neighbourhood is about 0.2 parsecs, or roughly 5,000 astronomical units, still an enormous distance by solar system standards but close by interstellar standards. This sparse distribution has implications for the likelihood of stellar encounters. Over the Sun's lifetime of about 4.5 billion years, no star is thought to have passed within 1 parsec of the Sun, and close approaches within 1/10 of a parsec are extremely rare events that might occur only once every few hundred million years. Even when such encounters happen, the distances involved are large enough that gravitational effects on the solar system are negligible. The orbits of planets are not disrupted, and the structure of the outer solar system, including the hypothetical Oort cloud of comets, remains largely undisturbed. The velocities of stars in the local neighbourhood provide additional information about galactic structure. Most stars move at speeds of a few tens of kilometers per second relative to the Sun, with directions that appear random when viewed locally but show patterns when averaged over larger volumes. These motions reflect the orbital motion of stars around the galactic centre, combined with smaller random velocities caused by gravitational interactions with other stars and with large-scale structures like spiral arms and molecular clouds. The Sun itself moves through the local neighbourhood at about 20 km per second relative to the average motion of nearby stars. This velocity is not large by galactic standards, but is significant when considering motions over millions of years. Over the past million years, the Sun has travelled about 20 parsecs through space, entering and leaving regions with different stellar populations. The stars we see as neighbours today were not neighbours in the distant past, and they will not be neighbours in the distant future. The local stellar population is constantly changing as stars move along their individual orbits around the galaxy. Brown dwarfs, objects too small to sustain hydrogen fusion but larger than planets, have been discovered within 10 parsecs only relatively recently. These objects are extremely faint, emitting mostly in the infrared, and they are difficult to detect even when nearby. Surveys using infrared telescopes have found several brown dwarfs within the 10 parsec volume, and it is likely that more remain undiscovered. The total number of brown dwarfs might rival or exceed the number of stars, though their contribution to the mass of the local neighbourhood is small, because individual brown dwarfs are much less massive than even the smallest stars. The completeness of the stellar census within 10 parsecs is high but not perfect. For bright stars and stars with large proper motion, the census is essentially complete. Every such star has been catalogued and its parallax measured. For faint red dwarfs and brown dwarfs, particularly those with small proper motion, gaps remain. New discoveries continue to be made, usually of very faint objects that were missed in earlier surveys or that lie in crowded regions of the sky, where they are difficult to distinguish from background stars. Each new discovery adds to the detailed picture of the local neighbourhood and provides additional data points for understanding stellar populations in the galaxy as a whole. The precision required to measure stellar parallax pushes against fundamental limits imposed by the nature of light and the structure of the atmosphere. Even a perfect telescope with flawless optics and no mechanical vibrations cannot measure angles arbitrarily small. Light behaves as a wave, and waves diffract when passing through apertures. The diffraction pattern created by a telescope's aperture places a limit on angular resolution that depends on the wavelength of light and the diameter of the telescope. For visible light and a telescope 1 meter in diameter, this diffraction limit is about 0.1 arcseconds. Larger telescopes have better resolution, but the improvement is proportional to diameter, requiring ever larger instruments to achieve marginal gains. Earth's atmosphere introduces additional complications that often dominate over diffraction. Air is not uniform. It contains pockets of different temperature and density, and these pockets move and shift constantly due to wind and convection. When starlight passes through these inhomogeneities, its path bends slightly, causing the apparent position of the star to wander. This effect, called atmospheric seeing, causes stars to twinkle when viewed with the naked eye, and causes their images to blur and dance when viewed through telescopes. On an average night at a typical observatory, atmospheric seeing limits angular resolution to about 1 arcsecond. On exceptional nights at the best observing sites, seeing can improve to half an arcsecond or slightly better, but it rarely approaches the diffraction limit of large telescopes. The seeing problem is worse for parallax measurements than for many other types of observation, because parallax requires comparing the positions of stars separated by significant distances on the sky. A target star must be measured relative to reference stars that are farther away and therefore have negligible parallax. If atmospheric turbulence affects the target star and reference stars differently, which it often does because they are in different parts of the sky, the resulting position measurements contain systematic errors that are difficult to correct. Averaging many observations helps reduce random errors, but systematic errors caused by differential atmospheric effects can persist even after extensive averaging. One approach to mitigating atmospheric seeing is adaptive optics, a technology that measures the distortions introduced by the atmosphere in real time and corrects for them using deformable mirrors. Adaptive optics systems can improve angular resolution dramatically, approaching the diffraction limit for large telescopes under good conditions. However, adaptive optics is most effective over small fields of view, typically a few arcseconds across. For parallax measurements that require comparing stars separated by arc minutes or more, adaptive optics provides limited benefit. The technology excels at producing sharp images of individual objects, but does not solve the problem of measuring relative positions across large angular separations. Another approach is interferometry, which combines light from multiple telescopes to achieve angular resolution equivalent to a much larger telescope. Interferometry has been used successfully to measure the diameters of nearby stars and to resolve binary star systems with very small separations, but it is not well suited to parallax measurements. The technique requires extremely precise knowledge of the positions and orientations of the telescopes involved, and maintaining this precision over the months or years needed to measure parallax is challenging. Interferometry remains a specialized tool for specific problems rather than a general solution for distance measurement. The limitations of ground-based observations motivated the development of space-based parallax missions. A telescope above the atmosphere is free from seeing and can measure angles limited only by diffraction and the mechanical stability of the spacecraft. The first such mission, Hipparcos, launched by the European Space Agency in 1989, revolutionized parallax measurement. Hipparcos was designed to measure stellar positions with an accuracy of about 1 millionth second, roughly 1,000th of an arcsecond. This precision extended the range of reliable parallax measurements from a few tens of parsecs to a few hundred parsecs, increasing the volume of accessible space by a factor of 1,000. Hipparcos operated for about 4 years, scanning the entire sky and measuring the positions of more than 100,000 stars. The mission's success depended on careful attention to systematic errors. The spacecraft spun slowly, completing one rotation every 2 hours, and it used this rotation to scan stars across its field of view repeatedly. By combining hundreds of observations of each star, Hipparcos achieved its target precision for most stars brighter than about 9th magnitude. Fainter stars had larger uncertainties, and the faintest stars in the catalogue, around 12th magnitude, had parallax uncertainties of several millionth seconds, limiting their usefulness for distance determination. The Hipparcos data revealed structure in the solar neighbourhood that had been suspected but not confirmed. Star-forming regions within a few hundred parsecs showed clear signs of recent activity, with groups of young stars moving together through space. The distances to these regions, now known with precision, allowed astronomers to calibrate other distance indicators and to test models of stellar evolution. The data also revealed that some stars previously thought to be nearby were actually distant and intrinsically luminous, while others thought to be distant were closer than expected. The successor to Hipparcos, Gaia, launched in 2013, represents another leap in precision. Gaia measures stellar positions with an accuracy of a few tens of microarcseconds for bright stars, roughly 10,000 times better than ground-based measurements and 10 to 100 times better than Hipparcos. This extraordinary precision extends the range of parallax measurements to several thousand parsecs for favourable targets. Gaia observes stars down to about 20th magnitude, much fainter than Hipparcos, and it has measured parallax for more than 1 billion stars, providing a 3-dimensional map of the Milky Way with unprecedented detail. Gaia's design incorporates several innovations to achieve its precision. The spacecraft carries 2 telescopes that observe different parts of the sky simultaneously, and it combines their observations to measure large angles with high accuracy. The spacecraft spins continuously, sweeping the telescopes across the sky and observing each star multiple times over the course of the mission. The spin axis precesses slowly, ensuring that every part of the sky is observed from multiple directions. This observing strategy allows Gaia to build up a self-consistent map of stellar positions that is tied to a small number of very distant quasars, whose positions are assumed to be fixed because they are so far away. The processing of Gaia data is a monumental computational task. Each observation must be corrected for the spacecraft's motion, for the bending of light by the sun's gravity, for the rotation of the Earth, and for numerous instrumental effects. The observations must then be combined to produce a consistent set of positions, parallaxes, and proper motions for each star. The process involves solving for billions of parameters simultaneously, using iterative algorithms that converge slowly toward a final solution. The data releases from Gaia have occurred in stages, with each release incorporating more observations and improved calibrations. The uncertainties in Gaia parallaxes depend on the brightness of the star and the number of times it has been observed. For the brightest stars, uncertainties are as small as 10 microarc seconds, allowing distances to be measured with precision better than 1% out distances of about 100 parsecs. For fainter stars, uncertainties are larger, and beyond about 1000 parsecs, most stars have parallax uncertainties comparable to the parallax itself, making distance estimates highly uncertain. Even with Gaia's impressive precision, the majority of stars in the Milky Way remain beyond the reach of direct parallax measurement. The cosmic distance ladder is a hierarchy of measurement techniques, each building on the previous one to extend the reach of astronomical observation farther into space. Parallax forms the foundation of this ladder, the only method that relies purely on geometry without requiring assumptions about the intrinsic properties of stars or other objects. Every other rung of the ladder depends on parallax for calibration, either directly or indirectly, and errors in parallax measurements propagate through the entire structure. The first rung above parallax involves main sequence fitting, a technique that uses the relationship between a star's colour and its intrinsic brightness. Stars spend most of their lives fusing hydrogen into helium in their cores, a phase called the main sequence. During this phase, a star's luminosity is tightly correlated with its temperature, which can be inferred from its colour. Hot blue stars are intrinsically bright, while cool red stars are intrinsically dim. By measuring a star's colour and comparing it to the known colour, brightness relationship for main sequence stars, astronomers can estimate its intrinsic brightness. Comparing the intrinsic brightness to the observed brightness then gives the distance. The critical step is establishing the colour-brightness relationship in the first place. This requires observing stars whose distances are already known from parallax. By plotting the colours and intrinsic brightnesses of these nearby stars, astronomers construct a template that can be applied to more distant stars. The accuracy of main sequence fitting depends entirely on how well the template is defined, and the template can only be defined using stars within the range of parallax measurements. Without parallax, there would be no way to determine the intrinsic brightnesses of stars, and main sequence fitting would be impossible. Main sequence fitting works well for star clusters, groups of stars that form together and lie at approximately the same distance. By observing the colours and apparent brightnesses of many stars in a cluster, astronomers can fit the entire main sequence simultaneously, reducing uncertainties and revealing the distance to the cluster as a whole. This technique extends the range of distance measurements to a few thousand parsecs, covering nearby star clusters and portions of the Milky Way's spiral arms. Beyond this range, individual stars become too faint to observe easily, and other methods must be employed. Cepheid variables provide the next rung on the distance ladder. These are stars that pulsate with regular periods, brightening and dimming in a pattern that repeats every few days to several weeks. The period of pulsation is closely related to the star's intrinsic brightness, a relationship discovered in the early 20th century by Henrietta Leavitt. Brighter Cepheids pulsate more slowly, while dimmer Cepheids pulsate more quickly. By measuring a Cepheid's period, astronomers can infer its intrinsic brightness, and by comparing that to its observed brightness, they can calculate its distance. The period-luminosity relationship for Cepheids must be calibrated using Cepheids whose distances are known from other methods. Parallax provides some of this calibration, though most Cepheids are too distant for parallax to measure directly. Instead, astronomers use Cepheids in star clusters whose distances have been determined by main sequence fitting, which in turn relies on parallax. The chain of dependencies is clear. Cepheid distances depend on main sequence fitting, which depends on parallax. Any error in parallax measurements affects the calibration of Cepheids, and thus all distances measured using them. Cepheids are bright enough to be observed in nearby galaxies, extending the distance scale beyond the Milky Way. The Andromeda Galaxy, the Large and Small Magellanic Clouds, and several dozen other galaxies within a few megaparsecs have Cepheids that can be individually resolved and monitored. By measuring the periods and apparent brightnesses of these Cepheids, astronomers determine the distances to their host galaxies. These distances are crucial for understanding the structure of the local group of galaxies and for calibrating techniques that reach even farther into space. Type 1. A supernovae provide the next major rung, extending measurements to distances of hundreds or thousands of megaparsecs. These stellar explosions occur when a white dwarf in a binary system accretes enough matter from its companion to exceed a critical mass, triggering runaway nuclear fusion that destroys the star. Because the explosion always occurs at approximately the same mass, Type 1 supernovae have similar intrinsic brightness, making them useful as standard candles. By observing a Type 1 supernova in a distant galaxy and measuring its apparent brightness, astronomers can estimate the galaxy's distance. The standardization of Type 1 supernovae is not perfect. Individual explosions vary in brightness by factors of several, and corrections must be applied based on the shape of the light curve and the color of the supernova. These corrections are derived empirically by studying nearby Type 1 supernovae whose distances are known from Cepheids. Once again, the calibration depends on Cepheids, which depend on main sequence fitting, which depends on parallax. The entire distance ladder rests on the accuracy of parallax measurements for stars within a few hundred parsecs of the Sun. The ladder continues to even greater distances using techniques like the Tully-Fisher relation for spiral galaxies and the fundamental plane for elliptical galaxies. These methods relate observable properties of galaxies, such as rotation speed or velocity dispersion, to intrinsic brightness. By measuring these properties and comparing to calibrations established for nearby galaxies, distances to more remote galaxies can be estimated. Each technique extends the reach a little farther, but also introduces additional uncertainty, because each step depends on calibrations from the previous step. At the largest scales, cosmological effects become significant. The expansion of space stretches light as it travels, shifting it toward longer wavelengths. This redshift can be measured and converted into a distance using models of cosmology, but the conversion depends on parameters like the Hubble constant, which describes the rate of expansion. Measuring the Hubble constant requires knowing distances to galaxies at various redshifts, and those distances come from Type 1 supernovae, which depend on Cepheids, which depend on main sequence fitting, which depends on parallax. The entire cosmological distance scale is ultimately anchored to parallax measurements of nearby stars. The importance of parallax to the distance ladder cannot be overstated. It is the only method that provides absolute distances without relying on assumptions about the physics of stars or galaxies. Every other method requires calibration, and that calibration traces back through however many intermediate steps to parallax. Improving parallax measurements improves the entire distance ladder. When Gaia measured parallaxes with 10 times better precision than Hipparcos, the effect rippled through every subsequent rung, reducing uncertainties in distances measured by main sequence fitting, Cepheids, Type 1a supernovae, and ultimately in the Hubble constant itself. Errors in parallax have historically caused significant problems in the distance ladder. Before precise parallax measurements were available, distances to Cepheids were uncertain by factors of 2 or more, leading to corresponding errors in the distances to galaxies. Early estimates of the Hubble constant varied by factors of 2 depending on which calibration was used, a discrepancy that created confusion about the age and size of the universe. As parallax measurements improved, these discrepancies narrowed, though tensions between different methods of measuring the Hubble constant persist even today. The structure of the distance ladder reveals both the power and the limitation of astronomical measurement. The power lies in the ability to extend measurements across scales ranging from parsecs to billions of parsecs, from the nearest stars to the most distant galaxies. The limitation lies in the accumulation of uncertainties. Each step adds its own error, and these errors compound. A 1% error in parallax becomes a 2% error in Cepheid distances, a 3% error in Type 1 supernova distances, and so on. The distance ladder is only as strong as its foundation, and that foundation is parallax. Standard candles are objects whose intrinsic brightness is known, or can be determined through observable properties. The concept is central to measuring distances beyond the reach of parallax because it transforms the problem of distance measurement into a problem of brightness comparison. If an object has a known intrinsic brightness, then its observed brightness depends only on its distance. The relationship follows an inverse square law. Double the distance, and the brightness drops to 1/4. Measure the observed brightness, compare it to the intrinsic brightness, and the distance can be calculated. The challenge lies in finding objects whose intrinsic brightness can be reliably determined. Stars vary enormously in luminosity, from red dwarfs that emit a tiny fraction of the sun's light to supergiants that outshine the sun by factors of millions. Without additional information, a star's apparent brightness provides no clue to its distance. It could be a faint object nearby or a brilliant object far away. Standard candles solve this problem by identifying classes of objects whose intrinsic brightness is either constant or can be inferred from other observable properties. Cepheid variables are standard candles of the second type. Their intrinsic brightness is not constant but can be determined from their pulsation period. The period is easy to measure. Observe the star over several weeks, record its brightness as it varies, and identify the time it takes to complete one cycle. Once the period is known, the period-luminosity relationship gives the intrinsic brightness. This relationship was discovered empirically by studying Cepheids in the Magellanic Clouds, two small galaxies visible from the southern hemisphere. All the Cepheids in a given galaxy are at approximately the same distance, so differences in their apparent brightness reflect differences in their intrinsic brightness. By plotting apparent brightness against pulsation period, Henrietta Leavitt found a clear correlation. The physical basis for the period-luminosity relationship was understood later. Cepheids pulsate because they are in an unstable phase of stellar evolution, where the outer layers of the star expand and contract rhythmically. The period of pulsation depends on the star's size and mass. More massive stars are larger and pulsate more slowly. More massive stars are also more luminous because they burn their nuclear fuel faster. The connection between mass, size, luminosity, and period creates the observed correlation between period and brightness. Calibrating the period-luminosity relationship required knowing the actual distances to some Cepheids. Parallax provided distances to a few nearby Cepheids. Though most were too distant for accurate parallax measurements even with hypocos, main sequence fitting of star clusters containing Cepheids provided additional calibration points. The distances to the Magellanic Clouds themselves had to be determined by other methods, before the Cepheids within them could be used as distance indicators to more remote galaxies. The entire process was circular in a sense, with each technique depending on others, but the consistency of results from multiple methods provided confidence that the calibration was approximately correct. Gaia's precise parallax measurements have refined the Cepheid calibration significantly. By measuring parallax for Cepheids within a few hundred parsecs, Gaia provided direct geometric distances that anchor the period-luminosity relationship without relying on intermediate steps. The improved calibration has reduced uncertainties in distances measured using Cepheids, with corresponding improvements in distances to galaxies and in the derived value of the Hubble constant. The fact that Gaia's parallaxes led to measurable changes in these fundamental quantities illustrates how critical parallax is to the entire distance scale. Type 1, A supernovae are standard candles of a different kind. These explosions occur in binary star systems where a white dwarf accretes matter from a companion star. When the white dwarf's mass approaches a critical limit, about 1.4 times the mass of the Sun, the pressure and temperature in the core become high enough to ignite carbon fusion. The fusion releases enormous energy, but instead of stabilizing the star, it triggers a runaway reaction. Within seconds, the entire star is consumed in a thermonuclear explosion that briefly outshines an entire galaxy. The uniformity of Type 1 supernovae comes from the fact that they always explode at approximately the same mass. The critical mass, called the Chandrasekhar limit, is determined by the balance between gravitational pressure and electron degeneracy pressure in the white dwarf. This balance is set by fundamental physics and does not depend on the star's history or composition. Because all Type 1 supernovae explode at the same mass, they release similar amounts of energy and reach similar peak brightnesses. This makes them useful as standard candles, though the standardization is not perfect. Individual Type 1 supernovae vary in peak brightness by factors of several. The variation is systematic rather than random, correlating with the rate at which the supernova brightens and fades. Supernovae that brighten and fade slowly tend to be intrinsically brighter than those that evolve quickly. By measuring the shape of the light curve, astronomers can correct for this variation, effectively standardizing the candle. After corrections, Type 1 supernovae have a dispersion in intrinsic brightness of about 10 to 15%, good enough for useful distance measurements. Calibrating. Type 1 supernovae requires observing them in galaxies whose distances are known from other methods. Cepheids provide the primary calibration, measuring distances to galaxies where Type 1 supernovae have occurred. These nearby supernovae establish the relationship between light curve shape and intrinsic brightness. Once calibrated, Type 1a supernovae can be observed in galaxies far too distant for Cepheids to be resolved, extending distance measurements to hundreds or thousands of megaparsecs. The technique is powerful but indirect, relying on a chain of calibrations that ultimately trace back to parallax. The discovery in the late 1990s that the expansion of the universe is accelerating came from observations of Type 1e supernovae at large distances. By comparing the observed brightness of these supernovae to their expected brightness based on redshift, astronomers found that distant supernovae were fainter than expected, indicating they were farther away than a non-accelerating universe would predict. This result depended critically on the calibration of Type 1, a supernovae as standard candles, which in turn depended on distances from Cepheids and ultimately on parallax. The entire chain of reasoning from parallax to the accelerating universe spans scales from parsecs to billions of parsecs. Other standard candles exist for specialized applications. RR Lyrae variables, stars similar to Cepheids, but older and less luminous, are used to measure distances to globular clusters and to map the halo of the Milky Way. The tip of the red giant branch, the brightest red giants in old stellar populations, provides another distance indicator for nearby galaxies. Planetary nebulae, the glowing shells of gas ejected by dying stars, have a brighter subset that can be used as standard candles. Each technique has its own calibration requirements and its own uncertainties, but all ultimately depend on parallax for their foundation. The reliability of standard candles depends on understanding the physics that makes them standard. For Cepheids, this means understanding stellar pulsation and the relationship between mass, size, and luminosity. For Type 1 supernovae, it means understanding white dwarf physics and thermonuclear explosions. If the physics is not fully understood, systematic errors can creep in, biasing distance measurements in ways that are difficult to detect. Cross-checks between different methods help identify such problems, but the cross-checks themselves rely on the assumption that parallax measurements are accurate. Beyond the range of parallax, even with the precision of Gaia, the vast majority of the Milky Way remains inaccessible to direct geometric distance measurement. The galaxy spans approximately 30,000 parsecs from edge to edge, and its disk extends to about 15,000 parsecs in radius. The central bulge, a dense concentration of old stars, lies about 8,000 parsecs from the Sun. At these distances, parallax angles are measured in microarc seconds or smaller, far below the detection threshold even for space-based observatories. Only the nearest few thousand parsecs can be mapped reliably using parallax, leaving most of the galaxy's structure to be inferred through indirect methods. This limitation creates a fundamental divide in galactic astronomy. Within parallax range, the three-dimensional positions of stars are known with precision. Distances are measured geometrically, and uncertainties are typically a few percent or better. Beyond parallax range, distances must be estimated using standard candles, spectroscopic parallax, or other techniques that rely on assumptions about stellar properties. These methods introduce larger uncertainties and potential systematic biases that can distort our understanding of galactic structure. Spectroscopic parallax, despite its name, is not a parallax measurement at all. It uses the spectrum of a star to infer its intrinsic brightness, then compares that to the observed brightness to estimate distance. The spectrum reveals the star's temperature and surface gravity through the strengths of various absorption lines. These properties correlate with luminosity, allowing astronomers to place the star on the Hertzsprung-Russell diagram, a plot of luminosity versus temperature. Once the star's position on the diagram is known, its intrinsic brightness can be read off, and the distance follows from the inverse square law. The technique depends on calibration. The relationship between spectral features and luminosity is established by observing stars whose distances are known from parallax. Stars within a few hundred parsecs provide the calibration sample, and the relationships derived from this sample are assumed to apply to more distant stars. This assumption is generally valid for main sequence stars, which have relatively uniform properties, but it becomes problematic for evolved stars like giants and supergiants, whose luminosities can vary significantly even among stars with similar spectra. Spectroscopic parallax can extend distance measurements to tens of thousands of parsecs, reaching the far side of the galaxy and beyond. The uncertainties are substantial, often 20 to 30% or more, but the method provides estimates where no other technique is practical. Large surveys have applied spectroscopic parallax to millions of stars, creating coarse maps of the galaxy's spiral arms, the distribution of young and old stars, and the motions of stellar populations around the galactic centre. These maps are statistical in nature, accurate in aggregate but uncertain for individual stars. The structure of the Milky Way has been revealed gradually through the accumulation of distance measurements at various scales. The disk, where most stars reside, is about 1,000 parsecs thick in the Sun's neighbourhood, but thickens toward the edges. Spiral arms wind through the disk, regions of higher density where star formation occurs more actively. The exact number and configuration of spiral arms remains uncertain because we view the galaxy from within, making it difficult to trace structures that extend across thousands of parsecs. Different traces, such as young stars, gas clouds, and dust lanes, suggest slightly different patterns, and reconciling these into a coherent picture remains an ongoing effort. The central bulge presents additional challenges. It is densely populated with stars, making it difficult to observe individual objects and measure their distances. Dust in the galactic plane absorbs visible light, obscuring the bulge from direct view. Infrared observations penetrate the dust more effectively, revealing a complex structure with multiple components. The bulge is not a simple spherical distribution, but appears elongated, forming a bar that extends several thousand parsecs from the galactic centre. The bar rotates, and its gravitational influence affects the orbits of stars and gas throughout the inner galaxy. The galactic halo, a roughly spherical distribution of old stars and globular clusters surrounding the disk, extends to perhaps 50,000 parsecs or more from the galactic centre. The halo is sparsely populated, containing only a small fraction of the galaxy's total stellar mass, but its extent makes it an important component of the galaxy's overall structure. Distances to globular clusters in the halo can be measured using RR Lyrae variables, which serve as standard candles for old stellar populations. These distances reveal that the halo is not uniform but contains substructure, streams of stars that may be the remnants of smaller galaxies that merged with the Milky Way in the distant past. The distance to the galactic centre is one of the most important distance measurements in galactic astronomy. It serves as a fundamental scale length for the galaxy and is needed to convert observed angular motions into physical velocities and distances. The measurement is difficult because the galactic centre is obscured by dust, and because there are no simple geometric methods that can reach across 8,000 parsecs. Instead, astronomers use a variety of techniques, including the motions of stars orbiting the supermassive black hole at the galactic centre, the properties of RS Lyrae variables in the central bulge, and the kinematics of gas clouds. The most precise measurements come from monitoring stars in tight orbits around the central black hole. These stars complete their orbits in a few years to a few decades, and their motions can be tracked with high accuracy using infrared telescopes equipped with adaptive optics. By fitting the observed orbits to Kepler's laws, astronomers determine the mass of the black hole and the distances to the stars. These distances, combined with models of the stellar orbits, give the distance to the galactic centre itself. Current measurements place it at about 8.1 to 8.3 kiloparsecs, with uncertainties of a few percent. This distance is crucial for understanding the galaxy's rotation and mass distribution. The rotation curve, which plots orbital velocity against distance from the galactic centre, reveals how mass is distributed throughout the galaxy. The Sun orbits the galactic centre at about 500,000 miles per hour, taking roughly 230 million years to complete one orbit. This orbital speed, combined with the distance to the galactic centre, constrains the total mass interior to the Sun's orbit. The derived mass exceeds the mass of visible stars and gas, indicating the presence of dark matter, an unseen component that dominates the galaxy's gravitational field. The transition from parallax-based distances to indirect methods occurs at different distances depending on the type of object and the precision required. For main sequence stars, parallax is reliable to about 1,000 parsecs with Gaia data. For Cepheids and other bright variables, parallax extends to a few thousand parsecs. Beyond these limits, distances become increasingly model-dependent, relying on assumptions about stellar evolution, chemical composition, and the uniformity of stellar properties across the galaxy. Each assumption introduces potential for error, and those errors accumulate as distance increases. The parsec, originally defined by the practical limits of parallax measurement, has become the standard unit for galactic distances even where parallax cannot be measured. Distances to the galactic centre, to spiral arms, to globular clusters, and to satellite galaxies are all expressed in kiloparsecs. The unit persists not because it describes a measurable parallax, but because it represents a convenient scale. 1 kiloparsec is roughly the thickness of the galactic disk. 10 kiloparsecs is the approximate distance to the galactic centre. 30 kiloparsecs spans the diameter of the main stellar disk. These round numbers in kiloparsecs correspond to the natural scales of galactic structure, making the unit intuitive for astronomers working on galactic problems. Kiloparsecs and megaparsecs extend the parsec into scales that describe not individual stars but entire galaxies and the vast spaces between them. A kiloparsec, 1,000 parsecs, is already large enough to span significant portions of the Milky Way. The Sun lies about 8 kiloparsecs from the galactic centre, placing it roughly halfway out in the disk. The galaxy's disk extends to about 15 kiloparsecs in radius, while the halo and its globular clusters reach to 50 kiloparsecs or more. These are distances where parallax has no direct application, yet the parsec remains the natural unit because it connects smoothly to the smaller scales where parallax does work. The Magellanic Clouds, 2 small irregular galaxies visible from the southern hemisphere, lie at about 50 and 60 kiloparsecs from the Milky Way. They are satellite galaxies, gravitationally bound to the Milky Way and orbiting it over hundreds of millions of years. Their distances were among the first extragalactic distances measured with any reliability, determined initially using Cepheid variables and later refined using other standard candles. These galaxies are close enough that individual stars can be resolved, allowing detailed studies of stellar populations and comparisons with stars in the Milky Way. The Andromeda Galaxy, the nearest large spiral galaxy, lies at approximately 770 kiloparsecs, typically rounded to 0.77 megaparsecs. This distance places it well beyond the reach of parallax, and even beyond most techniques that work within the Milky Way. Cepheid variables in Andromeda, discovered in the 1920s by Edwin Hubble, provided the first clear evidence that Andromeda was a separate galaxy, rather than a nebula within the Milky Way. The discovery fundamentally changed our understanding of the universe's scale, revealing that the Milky Way was just one of countless galaxies scattered through space. Andromeda and the Milky Way are the 2 dominant members of the local group, a collection of more than 50 galaxies spanning a region about 3 megaparsecs across. Most members of the local group are small dwarf galaxies, many discovered only recently as surveys have become more sensitive. The total mass of the local group is dominated by the Milky Way and Andromeda, with dwarf galaxies contributing only a small fraction. The gravitational interactions within the local group are complex, with smaller galaxies being tidally disrupted by larger ones, and streams of stars marking past mergers and ongoing accretion. Beyond the local group, distances to galaxies are measured primarily using standard candles, and, at very large distances, using the redshift of light caused by the expansion of space. The Virgo cluster, a large concentration of galaxies, lies at about 16 to 17 megaparsecs. It contains thousands of galaxies and represents a significant overdensity in the local universe. The gravitational pull of the Virgo cluster affects the motions of nearby galaxies, including the local group, which is falling toward it at speeds of several hundred kilometers per second. The Coma cluster, even more massive than Virgo, lies at about 100 megaparsecs. At this distance, individual stars cannot be resolved, and even bright Cepheids are too faint to observe. Type 1. A supernovae become the primary distance indicator, observable across the entire visible universe when they occur. The distances derived from these supernovae are less precise than those from Cephids, with uncertainties of 10 to 20%, but they extend measurements to scales where no other technique is practical. At distances beyond a few hundred megaparsecs, the expansion of space introduces a complication. Light travelling from distant galaxies is stretched by the expansion, shifting it toward longer wavelengths. This redshift can be measured spectroscopically, and it provides a proxy for distance. In a uniformly expanding universe, more distant galaxies have larger redshifts, and the relationship between redshift and distance is determined by the expansion rate and the geometry of space-time. The relationship is not linear because the expansion rate has changed over time, accelerating in recent epochs due to dark energy. Converting redshift to distance requires a cosmological model, a set of assumptions about the universe's composition and evolution. The Standard Model assumes the universe contains ordinary matter, and dark energy in specific proportions, and it describes how the expansion rate has changed since the Big Bang. The parameters of this model are constrained by observations of the cosmic microwave background, the distribution of galaxies, and the distances to Type 1a supernovae. The distances themselves depend on these parameters, creating a circular dependency that can only be resolved iteratively by finding the set of parameters that best fits all available data. At the largest observable scales, distances reach thousands or tens of thousands of megaparsecs. Galaxies at these distances have redshifts greater than 1, meaning their light has been stretched to more than twice its original wavelength. The light we observe was emitted billions of years ago, when the universe was much younger and denser. These galaxies provide a window into the early universe, revealing conditions that no longer exist nearby. The distances to such galaxies are inherently uncertain, not just because of measurement errors, but because the concept of distance itself becomes ambiguous in an expanding universe. There are multiple ways to define distance in cosmology. The comoving distance measures how far apart two objects are in a coordinate system that expands with the universe. The angular diameter distance relates the physical size of an object to its apparent angular size on the sky. The luminosity distance relates intrinsic brightness to observed brightness, and it is the definition most directly tied to observations of standard candles. These different distance measures diverge at large redshifts, and which one is appropriate depends on the question being asked. Despite these complications, the parsec and its multiples remain the standard units. Cosmologists speak of galaxies at hundreds or thousands of megaparsecs, galaxy clusters separated by tens of megaparsecs, and large-scale structures spanning hundreds of megaparsecs. The choice is partly historical, reflecting the continuity with measurements at smaller scales, but it is also practical. The parsec provides a scale that is neither too large nor too small for describing cosmic structures. A megaparsec is roughly the size of a small galaxy cluster. 10 megaparsecs is the scale of nearby clusters and voids. 100 megaparsecs describes the largest coherent structures in the universe. The relationship between parsecs and light years remains simple at all scales. 1 kiloparsec equals 3.26 thousand light years. 1 megaparsec equals 3.26 million light years. The conversion factor is constant, a consequence of the definitions. Yet even at megaparsec scales, astronomers prefer parsecs because the numbers remain manageable, and because the unit maintains continuity with parallax-based measurements, even though parallax itself ceased to be relevant thousands of parsecs ago. The use of parsecs at cosmological scales might seem like an affectation, a refusal to adopt a more intuitive unit, but it reflects the underlying unity of distance measurement in astronomy. Every distance from the nearest stars to the most distant galaxies is part of a single continuous scale. The methods change as distance increases, but the principle remains the same. Observe something whose properties are known or can be inferred, compare the observation to expectations, and calculate the distance. The parsec, defined at the scale where parallax works, extends naturally to scales where it does not because the entire distance ladder is built on the foundation it provides. The concept of cosmological distance becomes increasingly abstract as the scale expands beyond the local universe. Within a few hundred megaparsecs, distance retains an intuitive meaning. Galaxies occupy fixed positions relative to each other, at least over timescales short compared to their orbital motions. Measuring distance means determining how far apart these galaxies are in space, a straightforward extension of measuring the distance between stars. But at larger scales, the expansion of space itself begins to dominate, and distance becomes entangled with time in ways that challenge simple interpretation. Light from a distant galaxy takes time to reach Earth, and during that time, the universe expands. The galaxy was closer when it emitted the light than it is now. If we could freeze the expansion and measure the galaxy's current position, we would find it farther away than the light travel time suggests. The comoving distance accounts for this by calculating where the galaxy is now in a coordinate system that expands with the universe. But this distance cannot be measured directly because we observe the galaxy as it was in the past, not as it is now. The luminosity distance, which relates a galaxy's intrinsic brightness to its observed brightness, differs from the come-moving distance because the expansion affects both the energy and the arrival rate of photons. Each photon is redshifted, reducing its energy. The rate at which photons arrive is also reduced because the universe expands during the time photons are in transit. These two effects combine to make distant objects appear fainter than they would in a static universe at the same distance. The luminosity distance accounts for this dimming, but it produces values larger than the co-moving distance, sometimes by significant factors. The angular diameter distance, used to relate an object's physical size to its apparent angular size, behaves differently still. In a static universe, more distant objects appear smaller. In an expanding universe, this relationship holds at modest distances, but at very large distances, objects can appear larger than expected. This counterintuitive result occurs because light was emitted when the universe was younger and smaller, and the object subtended a larger angle then than it would at its current distance. The angular diameter distance reaches a maximum at a redshift of about 1 to 2, depending on cosmological parameters, then decreases at larger redshifts. These differing distance measures are not contradictions but reflections of the fact that distance is not a single well-defined quantity in an expanding universe. The appropriate distance measure depends on what is being calculated. For standard candles, luminosity distance is correct. For measuring the physical sizes of galaxies, angular diameter distance is appropriate. For describing the large-scale structure of the universe, commoving distance is most useful. Converting between these requires knowledge of the redshift and the cosmological model, introducing dependencies on parameters like the Hubble constant, the matter density, and the dark energy density. The Hubble constant describes the current rate of expansion. It is typically quoted in units of kilometers per second per megaparsec, indicating how much faster distant galaxies recede for each additional megaparsec of distance. Current measurements place the Hubble constant at about 67 to 73 km per second per megaparsec, depending on the method used. The discrepancy between different methods, sometimes called the Hubble tension, remains unresolved and is one of the most active areas of research in cosmology. The Hubble constant is not truly constant, but changes over time as the universe evolves. In the early universe, when matter was denser, the expansion rate was higher. As the universe expanded and matter became more dilute, the expansion rate decreased. More recently, dark energy has caused the expansion to accelerate, increasing the expansion rate again. The Hubble constant refers specifically to the current expansion rate, but understanding the history of expansion requires measuring distances and redshifts for galaxies at various epochs. Type 1, a supernovae provide the primary data for mapping the expansion history. By observing supernovae at different redshifts and measuring their distances, astronomers trace how the expansion rate has changed over billions of years. The results show that the universe transitioned from decelerating to accelerating expansion roughly 5 billion years ago, coinciding with the era when dark energy began to dominate over matter. This discovery, made in the late 1990s, was unexpected, and remains one of the most profound findings in modern cosmology. The measurement depends critically on the calibration of Type 1 supernovae as standard candles, which traces back through Cepheid variables to parallax. Errors in parallax propagate through this chain, affecting the inferred distances to supernova and thus the derived expansion history. Recent improvements in parallax measurements from Gaia have refined the calibration, but they have also contributed to the Hubble tension by shifting the inferred Hubble constant upward, increasing the discrepancy with measurements from the cosmic microwave background. The tension suggests that either one of the measurement methods is subject to unrecognized systematic errors, or the standard cosmological model is incomplete. Systematic errors could arise from incorrect calibration of standard candles, from unaccounted extinction by dust, or from selection biases in the samples of supernova used for calibration. An incomplete cosmological model might include additional forms of energy or matter, changes in fundamental constants, or modifications to general relativity that affect the relationship between redshift and distance. Resolving the tension requires better measurements across the entire distance ladder. Improved parallax measurements from future space missions will refine the calibration of Cepheids. Larger samples of Cepheids in galaxies with Type 1 supernovae will reduce statistical uncertainties. Better understanding of supernova physics will improve standardization. Alternative distance indicators, such as the tip of the red giant branch or gravitational wave sources, provide independent checks. Each improvement narrows the uncertainty and brings the different methods into better agreement, or reveals genuine discrepancies that point to new physics. At the very largest distances, approaching the edge of the observable universe, even the concept of a distance measurement becomes questionable. Galaxies at redshifts greater than 10 emitted their light when the universe was less than 1 billion years old. The light has been travelling for more than 13 billion years, and during that time the universe has expanded by a factor of about 11. The comoving distance to these galaxies is now about 30 billion light-years, or roughly 9,000 megaparsecs, but this distance is not directly observable. What we observe is the redshift and the apparent brightness, and we infer distance using a model that may or may not be complete. The edge of the observable universe, sometimes called the particle horizon, lies at a comoving distance of about 14,000 megaparsecs. This is the farthest distance from which light has had time to reach us since the Big Bang. Regions beyond this distance are not observable in principle because their light has not yet arrived. The observable universe is therefore a sphere centered on Earth with a radius of 14,000 megaparsecs, but this sphere is growing as light from more distant regions reaches us. The boundary is not a physical surface but a limit imposed by the finite age of the universe and the finite speed of light. The parsec, defined by the geometry of Earth's orbit and the parallax of nearby stars, extends through this entire range, from individual stellar distances measured in parsecs to cosmological distances measured in thousands of megaparsecs. The unit spans more than 9 orders of magnitude in scale, from the nearest stars to the edge of the observable universe. It connects the human scale of Earth's motion around the Sun to the cosmic scale of universal expansion, serving as a common language for describing distances that range from the comprehensible to the almost unimaginable. Every measurement in science carries uncertainty, and parallax measurements are no exception. The uncertainty arises from multiple sources: instrumental limitations, atmospheric effects for ground-based observations, the finite number of photons collected from faint stars, and systematic errors in calibration and data processing. These uncertainties affect not just the parallax measurements themselves, but every distance derived from them. And because parallax forms the foundation of the cosmic distance ladder, errors at this level propagate through every subsequent measurement technique. The uncertainty in a parallax measurement is typically expressed as a standard error, representing the range within which the true value is likely to fall. For a bright nearby star observed by Gaia, the parallax might be measured as 100 milliseconds with an uncertainty of 0.02 milliseconds, or 0.02%. This translates to a distance of 10 parsecs with an uncertainty of about 0.002 parsecs, equally precise. But for a fainter star at the same distance, the uncertainty might be 10 times larger, 0.2 milliseconds, giving a distance uncertainty of 0.02 parsecs, or 0.2%. The relationship between parallax uncertainty and distance uncertainty is not linear. Because distance equals 1 divided by parallax, the uncertainty in distance is approximately equal to the distance squared times the parallax uncertainty, divided by the parallax itself. This means that for a given absolute uncertainty in parallax, the percentage uncertainty in distance grows as the parallax becomes smaller. A star with a parallax of 10 milliseconds and an uncertainty of 0.1 milliseconds has a 1% distance uncertainty. A star with a parallax of 1 millisecond and the same absolute uncertainty has a 10% distance uncertainty. The percentage error increases inversely with parallax. This effect becomes severe for distant stars where the parallax approaches the measurement uncertainty. If a star has a parallax of 0.1 milliseconds with an uncertainty of 0.1 milliseconds, the distance is nominally 10,000 parsecs, but the uncertainty is so large that the distance could plausibly be anywhere from 5,000 parsecs to infinity. At this point, the measurement provides little useful information. The star is known to be distant, but how distant cannot be determined reliably. Gaia's catalogue includes many such stars, where parallax has been measured, but the uncertainty is comparable to or larger than the value itself. Systematic errors compound the problem. Random errors average out with repeated observations, but systematic errors do not. If the telescope has a slight misalignment, if the model used to correct for the spacecraft's motion is imperfect, if the reference frame defined by distant quasars has uncertainties, these effects introduce biases that affect all measurements in the same direction. Identifying and correcting systematic errors requires careful analysis of the data, comparison with independent measurements, and validation using stars whose distances are known from other methods. Gaia's data processing involves fitting billions of parameters simultaneously to create a self-consistent model of stellar positions, parallaxes, and proper motions. The process is iterative, with each cycle refining the estimates and reducing residuals. But the complexity of the model introduces opportunities for subtle errors. Correlations between parameters can cause biases in one quantity to affect others. The choice of reference frame, the treatment of binary stars, and the handling of stars with unusual motions all require careful attention. Even after extensive processing, some systematic errors remain, typically at levels of tens of microarc seconds for the best measured stars. The propagation of parallax uncertainties through the distance ladder is straightforward in principle, but complex in practice. Main sequence fitting uses parallax to determine the intrinsic brightnesses of nearby stars, and uncertainties in those brightnesses translate into uncertainties in distances derived for more distant clusters. If the parallaxes are systematically biased, the entire main sequence calibration shifts, and distances measured using main sequence fitting are biased by the same amount. A 10% error in parallax produces a 10% error in the distance scale, established by main sequence fitting. Cepheid calibration depends on distances to nearby Cepheids, some measured by parallax and others by main sequence fitting of clusters containing Cepheids. The uncertainties combine in quadrature, meaning the total uncertainty is the square root of the sum of the squared individual uncertainties. If parallax contributes a 5% uncertainty and cluster distances contribute another 5%, the combined uncertainty is about 7%. This uncertainty propagates to all distances measured using Cepheids, affecting measurements of galaxy distances and ultimately the Hubble constant. Type 1, a supernovae calibration, relies on observations of supernovae in galaxies whose distances are known from Cepheids. The uncertainties in Cepheid distances add to the intrinsic scatter in supernova brightness and to uncertainties in the light curve corrections. The combined uncertainty for an individual supernova distance might be 15 to 20%, dominated by the intrinsic scatter rather than the calibration. But for large samples of supernovae, the statistical uncertainty decreases, and the systematic uncertainty in the calibration becomes the limiting factor. If the Cepheid distance scale is biased by 5%, all distances measured using Type 1, a supernovae are biased by the same amount. The Hubble constant is particularly sensitive to distance scale uncertainties because it is measured by comparing distances to redshifts for a sample of galaxies. A 5% error in the distance scale translates directly into a 5% error in the Hubble constant. Current measurements give values ranging from about 67 to 73 km per second per megaparsec, a difference of nearly 10%. Part of this discrepancy may come from uncertainties in parallax, though other factors such as extinction by dust, selection biases, and differences in methodology also contribute. The impact of parallax uncertainties extends beyond the distance scale to other areas of astrophysics. Stellar luminosities depend on distances, and luminosities are used to test models of stellar evolution. If distances are wrong, the inferred luminosities are wrong, and models calibrated against incorrect luminosities will give incorrect predictions. Masses of binary stars can be determined from their orbits, but converting angular separations to physical separations requires knowing the distance. Errors in distance lead to errors in masses, which affect our understanding of stellar structure and evolution. Galactic structure studies rely on distances to trace the distribution of stars in 3 dimensions. If distances are systematically biased, the inferred structure is distorted. Spiral arms might appear more tightly wound, or more open than they truly are. The thickness of the galactic disk might be overestimated or underestimated. The distance to the galactic center, crucial for determining the mass distribution and rotation curve, depends on measurements that trace back to parallax. Errors in parallax affect the entire picture of how the galaxy is organized. Statistical methods can mitigate some uncertainties but cannot eliminate them. By averaging over many stars, random errors decrease and patterns become clearer. but systematic errors do not average out. If every distance in a sample is biased high by 10%, averaging over 1,000 stars still leaves a 10% bias. Detecting and correcting systematic errors requires independent measurements using different methods and comparing results to identify discrepancies. The process is iterative, with successive refinements bringing different methods into better agreement. The history of distance measurement is partly a history of reducing uncertainties. Each new technology, from photographic plates to charge-coupled device cameras to space-based telescopes, has improved precision and extended the range of reliable measurements. Hippocos reduced parallax uncertainties by a factor of 10 compared to ground-based measurements. Gaia improved on Hipparcos by another factor of 10 to 100, depending on the brightness of the star. Future missions may achieve further improvements, though the gains become progressively harder as instrumental precision approaches fundamental limits imposed by photon statistics and the granularity of matter. The importance of understanding uncertainties cannot be overstated. A measurement without an uncertainty estimate is nearly useless because it provides no way to assess reliability. A distance quoted as 1,000 parsecs might be precise to 1% or uncertain by 50%, and without knowing which, the value cannot be used confidently in further calculations. Properly propagating uncertainties through a chain of calculations ensures that final results reflect the true level of knowledge, neither overstating precision nor being unnecessarily conservative. The parsec remains counterintuitive because it inverts the relationship between distance and angle that humans experience in everyday life. When we look at an object, we instinctively understand that nearby objects appear larger and distant objects appear smaller. The angle subtended by an object decreases with distance in a predictable way. We use this relationship constantly, judging how far away something is based on its apparent size. A car that looks small is far away. A car that fills our field of view is close. The logic is direct. Distance determines angle. The parsec reverses this logic. It defines distance not by how large an object appears, but by how much an object's position shifts when viewed from different locations. The shift is measured as an angle, and this angle determines the distance. Smaller angles correspond to greater distances, maintaining the inverse relationship, but the conceptual framework is backwards from normal experience. We do not think of distance as something derived from angular shift. We think of angular shift as something that depends on distance. The parsec asks us to invert this intuition, to treat angle as primary and distance as derived. This inversion is not arbitrary, but reflects the realities of astronomical observation. Astronomers cannot measure distances to stars directly. They cannot send a probe to a star and measure how long it takes to get there. They cannot stretch a measuring tape across interstellar space. The only information available is light, and light provides two measurable quantities: intensity and direction. Intensity depends on both intrinsic brightness and distance, so it cannot determine distance without additional assumptions. Direction can be measured with high precision, and changes in direction over time reveal parallax. The parsec exists because direction is what astronomers can measure, and the unit is designed to reflect that fact. The choice of 1 arcsecond as the defining angle adds another layer of abstraction. An arcsecond is not a natural unit in any intuitive sense. It is 1/3600th of a degree, a division that traces back to Babylonian base 60 mathematics. The size of a degree itself is arbitrary, a consequence of dividing a circle into 360 parts for computational convenience. The arcsecond is thus twice removed from any physical reality, a subdivision of an arbitrary division of an abstract geometric concept. That this tiny arbitrary angle defines a fundamental unit of cosmic distance seems almost perverse. Yet the choice was pragmatic. 1 arcsecond represented the approximate limit of measurement precision in the 19th century when parallax was first successfully measured. Defining the parsec at this threshold meant that stars closer than 1 parsec would have measurable parallax, while stars farther away would have parallax too small to detect reliably. No star turned out to be closer than 1 parsec, so the parsec became a convenient reference point slightly beyond the distance to the nearest stars. It was a human scale in the sense that it matched human observational capabilities, even if it bore no relationship to human spatial experience. The mathematical elegance of the inverse relationship between parallax and distance provides some compensation for the conceptual awkwardness. The formula is simple. Distance in parsecs equals 1 divided by parallax in arcseconds. This simplicity is aesthetically pleasing to those who work with the mathematics regularly, and it reduces the cognitive load of converting between observable quantities and derived distances. But elegance in calculation does not translate to intuitive understanding. Most people do not think in reciprocals, and inverting a small angle to get a large distance feels unnatural no matter how simple the arithmetic. The confusion is compounded by the existence of the light year as an alternative unit. Light years make intuitive sense because they are based on time and speed, concepts that are familiar from everyday experience. Light travels at a fixed speed, and distance is speed times time, a relationship learned in elementary physics. A light year is how far light travels in a year, a definition that requires no geometric reasoning and no understanding of angular measurement. The fact that astronomers use parsecs instead of light years seems, to outsiders, like deliberate obscurantism, a refusal to adopt a clearer unit for the sake of tradition or professional insularity. The defense that parsecs simplify calculations falls flat for those who do not perform such calculations. For someone reading a popular science article, the simplicity of dividing one by parallax provides no benefit. They are not calculating distances. They are trying to understand how far away things are, and for that purpose light years are more accessible. The fact that converting parsecs to light years requires multiplying by 3.26 is a trivial inconvenience for readers, but represents an unnecessary extra step that obscures rather than clarifies. The persistence of the parsec reflects the divide between professional astronomy and public communication. Within the field, the parsec is indispensable. It connects directly to observations, simplifies mathematics, and maintains continuity with historical measurements. Outside the field, it is an obstacle to understanding, a technical term that requires explanation and never quite becomes intuitive. Science communicators face a choice: use parsecs and risk confusing their audience, or convert to light years and risk introducing errors or creating inconsistencies with professional literature. Neither option is satisfying. Some have proposed abandoning the parsec in favour of light years, at least in contexts aimed at general audiences. The argument is that clarity should take precedence over technical convenience, and that using units accessible to non-specialists would make astronomy more approachable. But such proposals ignore the fact that confusion about units is a relatively minor barrier to understanding astronomy compared to the conceptual challenges of grasping cosmic scales, the nature of light, or the evolution of stars. Replacing parsecs with light years would not suddenly make the universe comprehensible to people who struggle with its vastness. Others argue that the confusion surrounding the parsec is itself educational. Struggling to understand why astronomers use such a counterintuitive unit can lead to deeper appreciation of how astronomical measurements are actually made. The parsec forces engagement with the fact that distance is not directly observable, and that all cosmic distances are inferred rather than measured in any straightforward sense. This understanding is valuable, even if it comes at the cost of initial confusion. The parsec is not just a unit, but a window into the methodology of astronomy. The counterintuitive nature of the parsec also highlights a broader truth about scientific measurement. Units are not chosen for their intuitive appeal, but for their utility in specific contexts. The electron volt is not an intuitive unit of energy, but it is indispensable in particle physics. The astronomical unit is not obvious to non-astronomers, but it simplifies planetary dynamics. Every field develops its own system of units optimized for the problems it addresses, and those units often seem strange to outsiders. The parsec is no more or less counterintuitive than many other specialized units. It simply receives more attention because astronomy captures public interest in ways that particle physics or geophysics typically do not. The confusion ultimately stems from a mismatch between human spatial intuition, which evolved to navigate environments on scales of meters to kilometers, and the scales relevant to astronomy, which span parsecs to megaparsecs. No unit can bridge this gap entirely. Even light years, for all their conceptual clarity, describe distances so large that they remain effectively meaningless in experiential terms. Whether a star is 3.26 light years away or 1 parsec away, the distance is equally beyond human comprehension. The parsec does not make this worse, it simply makes the arbitrariness of our units more apparent.